screen. Okay, so for the students who were here, was it 2 days ago? Today is Tuesday, so it would have been yesterday. On Monday, Arizona time, which may be Tuesday, your time, depending on what country you're in. Do you have any questions from anything that we've covered up to this point? My understanding is Professor Alford dealt with basically basic elements of circuits, resistors, capacitors, inductors, and so on, talked briefly about voltage regulators and power delivery. So are there any questions? If there are, go ahead and put up your hand. Okay, and I'm going to go ahead and try to maximize this. Okay, so far I do not see any evidence of a question or questions. So Matt, if you see any questions from any of the students, then go ahead and let me know. I'm clicking on the chat window. Okay, yes, good night from Costa Rica. Perfect. It's evening here in Arizona as well, in the US, and it's 5:33 p.m. in Arizona. So, okay, so if there are no questions, let's go ahead and start with what we have so far. First of all, let me pull up, I'm going to pull up Canvas, look at the shell to see what Professor Alford had covered, and he had covered. Yeah, I'm having difficulty with the notification from Zoom, which is interrupting my window. Okay, there. So I'm expanding this. Okay, so based on what I see here on Canvas, Professor Alford has covered basic elements of circuits, an introduction to power supplies, and then he talked about voltage regulators. And since there aren't any questions from students that I can see, I am going to go ahead and start our session with the topics that I'm going to cover today. The first topic that I'm going to cover today deals with decoupling capacitors. So Professor Alford spoke about power supplies in the last session, which was yesterday. One of the key functions of a power supply in the context of semiconductor packaging is to provide power to the semiconductor chip and the fans and so forth as well, but primarily to the chip that is doing the logic. And this supply has to be very uniform. We don't want surges in voltage or drops in voltage, because if you have an increase or a drop in voltage, you will end up with inappropriate behavior of the devices in the chip. So for instance, it can throw off your calculations and so on. So to avoid that, and there's a variety of other issues that can also arise if you have a power supply that is not stable. So it's really important that you have a very constant voltage and a current that's delivered by the power supply that is appropriate to the load requirements of the chip. When the chip is not doing a lot of work, it will not draw a lot of current. However, when it's working furiously and doing a lot of work, what will happen is it'll request an increased amount of power from the power supply. So the purpose of the power supply, as Professor Alford very likely discussed yesterday, is to provide as much power as the chip needs and to provide it in such a way that the voltage is not spiking up or dropping, and also that the current that is requested by the chip is delivered by the power supply. Now, one of the key components of the power supply are decoupling capacitors. So we will speak now about decoupling capacitors. On this slide, on the right-hand side, we have a picture of a chip. Now, there is a blue arrow here on the left, and I've increased the size of my pointer, made it a big yellow arrow to make it easier to see. So you can see this arrow that's going out here. This arrow is pointing to electrolytic capacitors. So these capacitors are outside the chip. So here's the chip. The capacitors are outside. It's on the printed circuit board. And the purpose of these capacitors are to smooth out the power supply coming to the chip. In addition to these power supply, these capacitors, so these capacitors are larger. In addition to this, we see an arrow coming from the right, blue arrow. This is pointing to ceramic capacitors. Now, ceramic capacitors are better for high frequency operation, and they're also more efficient, but they are small and they're smaller, which is good, but they're more expensive than the electrolytic capacitors. So, so here are capacitors that's part of this power supply for the chip, and here are capacitors as well, intended to smooth the power that's coming to the chip, to smooth the voltage and so forth. And we'll talk about some of these reasons and how this works. So just as a reminder, we have a wide variety of backgrounds in our in the population that's attending this series of micro badges. We have students ranging from undergrad students who may not have much experience in any of these areas to professors from different universities who have experience in different fields. So my understanding is we have some professors with chemical engineering, some with material science, some with electrical engineering, and there may be other forms of engineering here as well. So for some of you, this information may be too basic. For others, you may not have seen this information. So as I'm presenting here, I have to teach at a level that everybody can understand. So my apologies if some of this stuff is too basic for you. And if it's not, and if I'm going at a level or at a speed that is faster or that needs more explanation than you need, feel free to ask a question. If there are a few questions, I'll handle them here during my presentation. If there are a lot of questions, then what I will do is have you put them into the chat, and I will focus on finishing the lecture and then coming back to answer those questions. Okay? So the purpose of decoupling capacitors. Now, why is it called a decoupling capacitor? What the decoupling capacitor does is it decouples high frequency signals from low frequency signals. So a high frequency signal is something that oscillates fast. A low frequency signal is something that's very slow. So ideally, we want to provide DC, direct current, to the chip. So direct current, as you know, is current that's flowing in one direction. Signals are typically alternating current. So the purpose over here, the first line, the purpose of the decoupling capacitor is to prevent electrical engineering energy from transferring between different parts of a circuit and to stabilize the power supply voltage. A significant component of this are the decoupling capacitors. What they do is they decouple separate parts of a circuit, for instance, or separate regions that are generating signals. So they isolate circuits. So the purpose of the decoupling capacitor is to decouple the alternating current. And just as a reminder, you know that an alternating current is a current where the charge travels in one direction, then travels back in the other direction. So it oscillates back and forth. So you want to separate out those signals from direct current signals. And as you know, a direct current signal is where the charges are traveling constantly in one direction, right? Or vice versa. There are some parts where you want the AC signals to come in. There are other parts where you want the DC signals to come in. Jose, I see that you have a hand up. Go ahead and ask your question.
Yes, Professor, just a quick question. I wanted to ask how probably it's a mathematical formula, but how do they calculate how many capacitors they need for a microchip?
Okay, that's an excellent question. We will talk about this as we go later on in these sessions. But very briefly, what you have to do is you have simulation software where you basically are simulating the behavior of your circuit. And as part of that simulation, and we'll see parts of this as we proceed, you can figure out for the kinds of signals that you expect to come into the system. Like, for instance, if there's a glitch in your power supply and the voltage suddenly spikes up or droops, what kind of a capacitor do you need to add in? Where do you need to add it in? And so that will determine the placement of the capacitor and the value of the capacitor. I know that's just a brief overview, right? But we'll see more of these elements as we proceed. Good question.
Thank you.
You're welcome. Okay, so isolating the circuits is one purpose. Reducing noise is another purpose, where what you're doing is you're shunting noise that comes from other circuit elements through the capacitor, which reduces its effect on the rest of the circuit. So what happens is if you have a spike in the voltage, now typically what will happen is when you have a higher voltage, there's a surge, you can have a surge of power that's coming into your chip. And so what you do is you keep these capacitors as a protection against that surge coming into the chip. So what the capacitor does when the surge comes in, it charges up. Instead of, it stores some of the electrical energy that's coming into the circuit from outside, rather than letting it go to the chip. And you know that if it goes to the chip, then it can destroy the chip if it's high enough, or alternatively, what it can do is it can cause a variety of like signal issues where the signal amplitude is too high suddenly, or alternatively, the signal timing gets changed, and then you end up with calculation errors, for instance, like 1 + 1 = 4, for instance. You can get errors like that if you don't control the noise of this sort coming in. And you also know that noise comes in from a variety of different sources. Every time you switch on a switch at home, for instance, so you've got the two wires that are coming in, and when the switch is off, it's like this. And then when you switch on the light in your room, you close it. And when you close it, what happens is there's a little bit of an arc, right? A jump in the current, which sends out an electromagnetic pulse into the environment. That electromagnetic pulse can be picked up by any wires that are anywhere in the vicinity. So if you have a microchip that has, and the microchip, has lots of wires both inside the microchip as well as in the printed circuit board on which the microchip is mounted, what happens is all of those wires, the electrons that are in those wires, when an electromagnetic signal, a pulse comes past and it's traveling past the wire. So if you have a positive field in this direction that switches negative and positive, for instance, if it's an alternating kind of a field coming in, then what happens is when you have a positive field like this, what that does is it causes the electrons to move accordingly back and forth in the wire. And so basically the wire acts like an antenna. Wire acts as an antenna for noise coming from anywhere, which can be the environment, the surroundings. It can even be other devices or other wires in the chip or in any of the components around the chip. This is why eliminating this is a very significant, I mean, it takes a lot of engineering. It takes a lot of intelligence. And that's why we need to have students and professors, of course, who understand these things and are able to engineer and provide the students to the industry that can then go ahead and do the simulations and so on to engineer the correct kinds of circuits to avoid this kind of noise. So one purpose, isolate the circuits. Another purpose is reduce the noise. These two are actually related, and provide a stable power supply. So the capacitors act as a buffer to provide clean and stable power to the components. Clean in the sense of uniform without spikes jumping up, either going up or going down. Along the same lines, one of the purposes is to maintain the voltage level, provide adequate power to an integrated circuit chip to maintain the voltage level in case of an input voltage drop. I'm trying to minimize the Zoom screen so I can see my slide. Okay, and also to prevent excess current. You don't want high levels of current flowing through the IC, through the chip. So you want to avoid voltage from spiking up. You want to avoid voltage from dropping down. And similarly, you don't want an excess current, sudden surge of current going through your chip. Because if you have a sudden surge of current, you can end up burning the components on the way to wherever the current is supposed to go. So all of these are the purposes of decoupling capacitors. So let's see, going to the next slide. This is basically the same picture on the left. On the right, I'm just making the point that decoupling capacitors are also called bypass capacitors. You'll sometimes see that term when they're used for higher frequencies. So for instance, with radio frequency chips and so on, or radio frequency. So for instance, you have radio frequency chips in your in walkie-talkies and radios and in cell phones and so on for the radio signal that's coming in, the cell tower signal that's coming in to the chip. So it's important to design circuits with capacitors that have higher tolerance than the highest voltage spike in the system. So if your system is running on, pick a number, 5 volts or 12 volts, you want to make sure that the capacitors are able to protect the chip from a sudden surge, which could be 50 volts instead of the 5 volts that you're asking for. And you may be aware that then there's a reason why you don't want a human Like if you were opening up your laptop, for instance, you don't want to be sticking your finger in at random on the laptop without grounding, right? An electrical ground that's linked to your wrist and then linked to ground any excess charge in you. Because if you don't do that, the spark that jumps from your hand, particularly in low humidity environments, can be 5,000 or 10,000 volts, which would destroy part of the chip, which that's the end of your chip. You'll have to get another one. Okay, moving on. So here's a cross section of a chip on a, okay, so here's a die. That's the silicon die here marked as die, and where I'm using my pointer. And then that is placed on top of a package, and that is placed on top of, in this case, like a motherboard. So where do decoupling capacitors come in? So, and why? So the die is over here. The die can request, right? So the die basically has logic circuits that are acting very fast. So depending on how many of the transistors are on for a particular logic operation, for instance, you can end up with a sudden surge in the requirement for current. So if you look at current as a function of time, the die could be operating, okay, these numbers are kind of high, but so let's say it's drawing 10 amperes. And what can happen is suddenly if there's a need for many of the logic, the transistors switch on, you can end up with a surge to 50 amperes in a very short period of time. Now, normally, so the load current over here on the left in a microprocessor can ramp up very quickly within a few clock cycles. The clock cycle, as you know, is where there's a clock signal that says it's pushing forward the operations of the microchip, and it tries to coordinate the operations of the microchip across the entire microchip. It's just like us and the second hand on a clock that's ticking, right? So that's the clock signal. So within a few clock cycles or signals, the load current in a microprocessor can jump a lot, whereas a conventional VAR stands for voltage regulator, takes about 100,000 cycles in a 3 gigahertz microprocessor to respond to a typical load current ramp request. So there's a big, so over here you have a voltage regulator, and what happens is the chip is asking for a current at this rate much faster. The voltage regulator is not able to deliver at the same rate. It takes quite a while for it to do so. So what you do in part is you store electrical energy when you can in a variety of capacitors through the chip to be able to deliver current, voltage, electrical energy faster when needed. So that's one function in addition to the previous functions, which is to decouple the chip. So here we can see that on the printed circuit board, on the left-hand side, we have a onboard voltage regulator, and then you have bulk capacitors. Then here you have MB as motherboard. So I've expanded the acronyms. You got motherboard capacitors here. So VR here over on the left is the voltage regulator. So here we have motherboard capacitors that are closer to the die. Then here we have the chip. So from the chip here, we have all of these current lines, right? Or power lines and so forth. The red lines and the green lines, they come through the package up to the die. So here's the package. Now here we have die side capacitors. You can have capacitors that are built on the package that are closer to the die here and here. Then in addition to this, you can have land side capacitors. This is underneath the package. So you've got additional capacitors here that can provide charges as needed or protection as needed to the die. And so you can have these handling different parts of the circuit. This will likely handle the signals coming to this part. This will handle signals to this part, and here to the middle of the die, for instance, right? So that's typically how this is laid out. Let's go on to the next. So in the real world, so in an ideal world, you may know already that from Professor Alford's lecture that a capacitor is commonly just simply two metal plates that are close to each other, and you will have some kind of a dielectric in between that insulates the charge from leaking from one plate to the other plate. And then you've got power lines coming out, or leads or electrical wires coming out of the plates. So the plates, they provide a capacitance, and it's called a capacitance because it has a capacity to store electrical energy. That's what it's doing, right? Now, in the ideal world, that's all it does. But in the real world, nothing is as ideal as we might hope it to be. So the capacitor, and this Professor Alford may have discussed the fact that a capacitance has this symbol right over here with two parallel plates with a gap between them. You're storing positive charge on one plate and negative charge on the other plate. In the ideal world, that's all there is to a capacitance. But in real life, what happens is, in addition to that, okay, these two symbols need to be switched. ESL is equivalent series inductance, and ESR is equivalent series resistance. So what happens is, this symbol is a symbol for a resistor. So what happens in addition to the capacitance, the wires of the capacitor itself has the equivalent of a resistance that resists the flow of current. So the label here really should say ESR, not ESL. And the label here to match this symbol should be ESL, which is the equivalent series inductance. So Dr. Alford may have talked about the fact that what the capacitor does is it charges electrical resistivity and it resists a change in voltage change. Like if there's a sudden spike in voltage, the capacitance will resist that change. A resistor, typically what it does is it resists the flow of electrons or other charges, but typically in most circuits, we're talking about electrons. Yes, outside of transistors, we're typically talking about electrons. Now, an inductance, what it does, or an inductor, what it does is it stores magnetic energy. While this charges electrical energy, this is storing magnetic energy in the form of a magnetic field. And what this does is it resists sudden changes in current. So in real life, a capacitor behaves as if it's a capacitance in series with a resistance in series with an inductance. So the behavior of most capacitors is like this. If you look at impedance, now Professor Alford may have talked about impedance, but I will mention that impedance is basically the device impeding. It's the equivalent of resistance, but applied to alternating current. So resistance typically applies to a direct current. So if you've got current flowing in one direction, a resistor resists the flow of the current for a direct current. An impedance, what it does is it's taking in the effect of an alternating current or a high frequency signal, and it provides an impedance, that is a resistance, to the changing of the current back and forth. So impedance has two components, the capacitive component and the inductance component. So if we look at the frequency of the signal coming in, at low frequencies on the left-hand side, capacitance dominates the impedance. So this dominates. As we increase the frequency to going to very high frequencies, what happens is the inductance takes over. So here, the electrical field storing energy is dominant. Here, the magnetic field storing energy is dominant. So this is the behavior of a capacitor typically when you look at its impedance as a function of frequency. So this slide describes a little bit of what's going on here. So on the left-hand side is what we saw on the previous slide. And here is the explanation that says that electrical impedance is a measure of how much a current resists the flow of alternating current. It is like resistance, but it's more complex. It's more complicated because it applies to circuits where voltages and currents are changing with time, like in alternating current circuits. So there's a difference between impedance and resistance. In simple direct current circuits where the current is all flowing in one direction, we talk about resistance, which opposes the flow of current. So Professor Alford may have talked about the fact, like when you think of a current, the voltage is like it's not really, but it's like a force. You can think of it like a force that's pushing, like the pressure that's pushing the water forward in your faucet. So the voltage is pushing you can think of a voltage pushing the electrons or the charges forward. Resistance resists that flow, so it pushes backwards. So the current, which is proportional to the number of charges that's traveling through per second, is directly proportional to the forward pressure, that's the voltage, and inversely proportional to the backward pressure, that's the resistance. That's one way of understanding that. So we talk about that in direct circuits, in direct current circuits. However, in AC circuits, we talk about impedance because it accounts for both resistance and another property called the reactance. The reactance comes from other components that we're now talking about, like capacitors and inductors, which oppose changes in current and voltage as a function of time. So we're now on the next slide. The left side is the same as what we have seen, and we're continuing to talk about impedance, but now adding in a formula. Impedance Z over here is a combination of the resistance and the reactance. It's usually expressed as a complex number that has two parts, a real part, which is the resistance R, and an imaginary part, which is called the reactance here. So the impedance is a real term, resistance, plus J, which is the imaginary unit, multiplied by X, where X is the reactance. So J is the imaginary unit. It represents a 90-degree phase shift between the voltage and the current. If you did not have J, what would happen is Z would just, if you didn't have the reactance part, Z would be just equal to the resistance. So that's in this, like if the current is trying to travel in this direction, the resistance is basically pushing back in the same direction. When you add in J, what happens is you're now talking about a phase shift between the voltage and the current. So and it's talking about a 90-degree phase shift. So the voltage, if the voltage is going up and then coming down, what happens is the current lags by 90 degrees, or it can lead depending on your capacitance and inductance. So continuing with this topic, real world capacitors are not ideal. The reactance, we said there are two types of reactance. The first is capacitive reactance, which is given by X sub C. Capacitors, as I mentioned, resist changes in voltage, and the formula for the reactance, the capacitive reactance, XC is equal to 1 divided by 2 pi FC, where F is the frequency of the AC signal and C is the capacitance of the capacitor, typically in farads, microfarads, picofarads, and so on. So here we can see, because F, the frequency is in the denominator, as the frequency increases, the capacitive reactance decreases. And that's the reason why we saw the capacitance dropping as the frequency went up. In contrast to that, we have the inductive reactance, which is X sub L, and inductors resist changes in current. Okay, remember that capacitors resist changes in voltage. Here, the inductor resists a change in the current. So XL is equal to 2 pi FL, and here we can see that the reactance, the inductive reactance, is proportional to the frequency. So F is the frequency and L is the inductance. So as the frequency increases, the inductive reactance increases. And that is the reason for what we saw on the previous slide. We saw that the impedance, which is a combination of the capacitive reactance and the inductive reactance, at low frequencies, it's dominated by capacitance. And as the frequency goes up, because it's in the denominator, the capacitance drops. However, as you go to increasing frequencies, what happens is, since the inductance, the reactiveness, the reactance due to inductance is proportional to the frequency, you can see that that inductance increases, and that explains this behavior, right? Okay, so here is a picture of a capacitor. So on the right-hand side is the big picture view of the capacitor. Now, if you were to take a cross-section of this capacitor, it would look like this. And if you zoom into the center of the capacitor, you can see there's a bunch of separate plates. So there are plates. So there's like a metal plate, an insulator plate, a metal plate, insulator plate, and so on. So that's typically what you see in things like ceramic capacitors, and any of the capacitors, actually. It's just that you choose different materials depending on, like if you use a ceramic capacitor, the ceramics are more expensive than electrolytic capacitors. And so, but you're able to get higher capacitance in a smaller area by getting these plates very close to each other and making very thin dielectric. And so by doing this, you can have a high capacitance number in a small form factor in a very small size that you can actually put directly on the chip, or you can put it immediately above the chip and so on. So in this case, you can see the current loop that's described here. Current is traveling in the line at the bottom, then going up here through the capacitor, and then coming back out. So since it's completing a loop, that creates a loop area where current is going in a loop, and that creates inductance in addition to the capacitance, the charge storage and release. The effective area of the capacitor depends on the capacitor mounting and the landing pads. So that's down here, where the landing pad is the pad down here onto which you're putting the capacitor and making the contact. Looking at on-die capacitors. So there are different kinds of on-die capacitors here for a few examples. The expansions. So here we have a MOS capacitor. MOS stands for metal oxide semiconductor, which basically means you have a metal layer. Beneath this, you have an oxide layer. And beneath this, you have a semiconductor. So when you bring a charge here using the semiconductor and you apply voltage across this, what can happen is you end up with charge storage here, like positive charge here and negative charge there separated by the oxide, and that creates a charge separation. There's a force that attracts the positive and the negative, as you know, and this causes storage of electrical energy. So that's a MOS capacitor. The next, we have a MIM capacitor, which historically stood for metal insulator metal capacitor. So here you can see, it's difficult to see here. There's a metal plate and then a thin oxide plate, or an insulator plate, then a metal plate, insulator plate. So this is a cross section. It looks like a cross section transmission electron micrograph, where you're basically taking one of these capacitors, making a very thin cross section and sending electrons through it to get the image. So when you get the image here, you can see that there's a plate on top. And to me, that it could be a metal. It could either be polysilicon that's doped, silicon that's highly doped, or it could be, it does not look like tungsten to me. It could be another polycrystalline metal like aluminum or something of that sort, or copper, or it could be tungsten. Then beneath that, there's a darker line, which is a dielectric. Then beneath that, there's another metal plate, then a dielectric, then a metal plate. So what you're doing here is you're creating a capacitor here with metal, any of the metals I mentioned, then an insulator, and then metal, then insulator and metal, and so on, similar to here. That's a MIM capacitor. And so these two are forms, and this is another kind of capacitors that you put on the die. They're literally on the die, or they're built into the die. So here we have something that's called an ICAP DTC. ICAP just stands for capacitor. DTC stands for deep trench capacitor. So in this case, what happens is, so you can call it a trench capacitor or a deep trench capacitor, and this is built into the silicon interposer that's placed beneath the silicon die. So there's a silicon die, silicon interposer, then you've got the package. So you can build these capacitors into the silicon interposer that you're putting between the die and the package. So here, what you're doing is you etch a very deep trench. So this trench can be 5 microns deep or deeper. And there's a small opening. And then what you do is you've got a trench. In that trench, you deposit a thin oxide typically as an insulator. Then you put a thin metal, then an insulator. And what happens is, and then another metal. And then what happens is, so those go over this, and that can create a capacitor that has a large area inside a very small lateral form factor. So that means you can increase the capacitance for a very small lateral space. So that's the purpose of these. Okay, so now previously we looked at cross sections. Now we are looking at top-down views. Looking at the top-down, here's a package with die-side capacitors. So this is the die. So this whole thing is the package. Then here is the die, one die, here's another die. And these little white blobs, some of these blobs are actual capacitors that are placed on top of in the package or on the package board. And they are die side with the capacitors. You can also have, as I mentioned, you can also have capacitors. So these capacitors are on the side of the die, right? They're on the board on the side of the die. But you can also have land side capacitors that are beneath the die. And so you take the die and you flip it upside down. And when you flip it upside down, here are the contact pads or pins or balls of the die. And then here beneath the die, you're actually adding more capacitors. So looking at MB stands for motherboard. I have that wherever I wrote that on a previous slide. Ceramic versus electrolytic capacitors. So we have seen this image before, but now we have the labels, electrolytic capacitor here, which is off of the die. It's not on the die, it's on the package, but adjacent to the die. And here we have ceramic capacitors that are actually built into or on top of the die. So electrolytic capacitors are made with a positive anode and an oxide layer. So there's an anode, an oxide layer, and then an electrolyte. The anode is typically made of a metal, example, aluminum, tantalum, or niobium, that forms a thin oxide layer through anodization, right? It's basically a form like you send a current and you get it to oxidize, which acts as the capacitor's dielectric. So you can get very thin dielectric on top and between the electrolyte and the metal. So the electrolyte then covers the oxide layer and acts as the negative cathode. The benefits of these electrolytic capacitors are high capacitance, very thin dielectric layer, and large area. So they're large. In contrast, ceramic capacitors, they have alternating layers of ceramic and metal. And charge separation in both of these, separation of charges, positive versus negative, is used to store the energy. So examples of some of the ceramics are Mg, and so magnesium niobium oxide. So I've dropped the subscripts, right? For ease of representation, zinc niobium oxide, magnesium tantalum oxide, zinc tantalum oxide, zinc magnesium titanium oxide, zirconium tin titanium oxide, and barium titanium oxide. So any of these ceramics can be used, and they all have slightly different properties. Of course, the more expensive ones tend to have greater charge storage density. That's the motivation to look at more expensive capacitors. Okay, so look, we've seen this image before, except that now there are different text tabs here. So as I mentioned earlier, VR is voltage regulator, MB over here stands for motherboard, DSC over here stands for die side capacitor, LSC stands for land side. That's here, these ones, capacitor. As we mentioned, go ahead, Jose, I see a question.
Oh, sorry to interrupt, Doctor.
Okay.
I see that there's always like a safe distance between capacitors. I guess if they put them together, we will have an electromagnetic problem right there because or it's
Yes.
just
Yeah. One of the anytime that's a good point. Anytime you have two devices of any kind, like when you bring them together, what happens is the fields in the currents that are traveling through the wires, right? The currents traveling through the wires are creating magnetic fields and electric fields. So those fields, if you bring the lines close together, the field from one line can create a crosstalk signal in the next line.
Exactly.
And so, yeah, and as you do that, it becomes increasingly difficult to separate out the, like you're trying to accomplish one thing with one device, but in the process of accomplishing that one thing, you're screwing up something that another device is trying to accomplish. So you're right. So that is a very serious concern that has to be addressed through things like simulation. And so they will, there'll be simulation engineers who literally move these devices, and they will have like design principles that says that you're not allowed to put, like a certain kind of device cannot be put closer than a certain distance from the other devices around it. Good question.
Great. Thank you.
You're welcome. Okay, so we talked about the fact that the die, when it's doing its logic operations, for instance, can suddenly ask for a high current. When it suddenly asks for a high current, the voltage regulator, the power supply, it's going to take a long time to respond. And so what happens is you need to have storage of energy closer to the logic operating die to respond as quickly as the die asks for electrical energy. So when you have a sudden spike in the requirement from the die capacitors, those that you build into the die, are the first to respond. The package capacitors, so the capacitors that you built into the die are the first to respond. Then package capacitors are the next to respond. And typically as a function of distance, so you'd have the land side capacitors responding over here, the die side capacitor on the left and right responding to operations in this area, for instance. So the motherboard, ceramic capacitors are the next so motherboard, but if you have ceramic capacitors, they're faster than the electrolytic capacitors. And then the voltage, okay, the bulk capacitors come after the motherboard ceramics, and then after that is the voltage regulator. So that's what you're trying to do is when there's a sudden spike in demand, you try to have electrical energy sources that are as close to the location of the demand. That'll supply first, then they run out of energy, and then the next set of capacitors, then the next set of capacitors. That chain progresses outwards. And by doing this, so a lot of design goes into building in the correct amount of these capacitors at the correct locations on the die to begin with, and then on the motherboard, on the package, right? The package as close to the die near the locations that are demanding the current, and then on the motherboard itself. So that gives you an idea of the significance of this. So in summary, microprocessor current can ramp up quickly in a few clock cycles, as we saw. Most microprocessor power delivery networks use multiple stages of decoupling capacitors to handle the short-term current flow before the power supply on the motherboard can respond. There are many factors that we need to consider when choosing what kind of a capacitor to use and also where to place it. So the size of the capacitor, both in terms of its capacitance as well as its physical size, the parasitic resistance and inductance of the capacitor, variation in the capacitance value, which changes as a function of frequency, we saw, and the cost are some of the key factors that influence the choice of capacitors. In general, there's a trade-off between cost versus size. The bigger the size, the cheaper the cost. The bigger the size, the higher the cost, the better the efficiency or the speed of response and so on. So you don't want to make a cell phone, for instance, that is $1,000 that nobody will buy. I mean, just as an example, right? Or a laptop that's going to cost you $10,000 because nobody will buy it. It could be the best laptop in the world, but nobody can afford it. So there's a trade-off where you will typically try to make the market, people buying things, has certain psychological purchase points. So $500, at least in the US, and then that'll correspond to whatever numbers in each country. Similarly, in whatever you look at is whatever country you're in, you'll find that things that tend to be priced in certain round numbers. So 500 units of your local currency versus 1,000 units of your local currency versus 5,000 units of your local currency. You'll see different quality of gadgets that are sold at each of those categories. And so what you might do as a manufacturer is be able to sell. So for instance, you may know that gaming laptops tend to be higher performance. And so they're more expensive than regular, like school laptops. You can get them for much cheaper now. And they are not as powerful as gaming laptops are, for instance, or computers that are using for things like AI. Servers that you use for AI have much higher logic demands, or servers that you use for things like crypto mining also have much higher demands. Okay, so I'm not going to go over these. So just to give you I'm not going to answer these questions is what I mean, but I'm just giving you an overview of the questions that I put at the end of each of these slide presentations for you to think critically about this topic. And the questions are intended to push your knowledge beyond what we have covered in this course. You can always do research online to answer these questions. Some of these you'll be able to answer yourself. Some of these you'll need to do some additional research, either using textbooks or research online. So the first question, in what ways do decoupling capacitors contribute to maintaining stable voltage levels in high-speed digital circuits? We've covered the answers to this. But you're being able to answer this, for instance, it's a good idea for you to have a notebook that you write down each of these critical thinking questions and you answer them to the best of your ability. And that'll help you to reinforce this information in your mind. And then later, because many of your faculty, if you teach this to students in the future, that'll help you as well. And you can do the same thing with your students. Now, how would circuit behavior change if these capacitors were not included? Right, that's something that should be evident from this presentation. How does the placement and selection of decoupling capacitors influence their effectiveness in stabilizing voltage particularly in circuits with high frequency components of fluctuating loads. The fourth question is considering different types of decoupling capacitors. How would the choice of capacitor type, example, ceramic or tantalum capacitors, tantalum oxide, affect the overall stability and performance of the circuit under various operational conditions? So just something for you to think about, right? So I'm going to go ahead and end this particular mini lecture here and move on to the second one, screen sharing stop. So
Hi,
it's about
Professor.
Go ahead.
We have different questions, the chats.
Okay, so there are questions in the chat.
Yes.
Okay, let's look at them. Thank you for bringing that to my attention. Okay, scrolling down.
You're
Okay,
welcome.
first, thank you. Yeah. Okay, what are the advantages of using more ceramic capacitors on a PCB in terms of frequency response and signal amplitude? The ceramic capacitors, now, they are more expensive than the electrolytic capacitors. They respond quicker. They're better for high frequency applications. So if you use more ceramic capacitors on the PCB, you're going to make your system more expensive. That's a disadvantage. The advantage is you have better frequency response. So, and signal amplitude, what you do is basically you have to make sure that you have enough capacitors, whether they're electrolytic or ceramic. So you can handle the signal amplitude just by increasing the number of capacitors of whichever type. But the more ceramic capacitors you use, the more expensive your motherboard is to be. And on the motherboard, typically you have more room, right? So on a PCB, printed circuit board, you have more room. And so you have more room to put more of the cheaper capacitors. So if your target audience, your target market, if they are price sensitive, then you would go with more of the electrolytic capacitors on the motherboard, on the PC, the printed circuit board. However, if your target market is not price sensitive, like a lot of gamers, it's like it's their hobby, it's their passion. So as a result of this, a gamer is more likely to pay more money for higher performance. So if you want more higher performance at a higher price, you can use more ceramic capacitors. Now, when you're actually putting capacitors on the silicon die, you don't have a choice of putting electrolytic capacitors because you're limited in terms of room, for instance. Okay, that's one question. What are the red line and green line conductive lines? Yes. So that is just an illustration. It's an illustration. There are different lines that come into, so it's not intended to specifically link to a particular kind of line, but just point out that there are different kinds of line coming from the voltage regulator to the chip. So typically in terms of the chip, you have ground lines that are coming in, you have power lines that are coming in, and then you have signal lines that are coming in. So really there should be more than two colors. Like instead of just red and green, there should be like maybe 10 colors because of the fact, depending on the complexity of the chip. Because not only do you have ground lines coming in, right? So you know that the current goes to the power and then goes through the device to the ground plane and comes back to your power supply or whatever, right? So you need to have lines coming in for ground planes. So you've got a ground plane, which is a sheet that is all held, let's say it's 0 voltage. And then you have connections to that 0 voltage sheet, for instance, to transfer the ground voltage to different parts of the circuit. Then you have power lines that are coming in at certain voltages, at a certain voltage. And that can go to a power, either power buses, which are fat lines, much fatter than the signal lines, that convert, that travel, that where the power travels down to the circuit. Or you can even have a power plane where you have a sheet of metal that is acting as the power source to all the devices that are above it. But there are disadvantages with that. Now, the reason why you'd have multiple power lines and multiple ground lines is because of the fact that different parts of the chip operate differently depending on their function. And what you want to do is you want to isolate, you don't want, so the ground plane could shift, for instance, for some reason. The power plane can also shift in voltage for some reason. So you may have a reason to have different sections of the chip that are fed by different power lines and by different ground lines, because you don't want crosstalk in terms of misbehavior of the power lines or the ground lines based on the function of one part of the chip. So really, in real life, you'll have much more than just the green and the red. But this was just illustration. Let's see the next question. When multiple decoupling capacitors are connected to the power pins, does the total capacitance of the circuit increase? How does it affect this? So it depends. As you probably, okay, we haven't gone into this. Those of you who have experience in electrical engineering know that, like, if you take resistors and you add them in series, the total resistance is the sum of these resistances. Whereas if you add the resistors in parallel, then the total effective resistance is the harmonic mean. That is 1 over the total resistance, is 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance, and so on. In the case of capacitances, that is inverted. So depending on how you hook up the capacitors, you will end up with the capacitors adding up in capacitance or acting as harmonic, basically a harmonic mean, where 1 divided by the total resistance, capacitance is 1 over the first capacitance plus 1 over the second capacitance, and so on. That's beyond what I've talked about here. The answer to your question depends on how those capacitors are wired up. So the effective capacitance of the circuit is the sum of all the capacitors that are in the circuit, but not just linearly added up. Some of them are linearly added up, some of them are harmonically added up. So linear addition will increase the effective capacitance. Harmonic addition will lower the effective capacitance because it's providing more paths, if you will. So the answer to your question is it's complicated and it depends. So you actually have to do those kinds of calculations given the circuit design that you're working with. Okay. Okay, what are the different effects of ceramic and electrochemical capacitors when put on the circuit for decoupling? That I have already answered, which is basically that you can have better high frequency response with the ceramic, and you can also have a smaller form factor. That is, the capacitor itself is physically much smaller, so you can add in more capacitors as needed, but the price goes up, right? Okay, good questions. Let's start to take a break every hour. So we started at 5:30. So it's now about 50 minutes, 55 minutes. So what do you think? So it's 6:24 here, Arizona time. Let's take a 6-minute break, and then we'll start again at 6:30, at 30 minutes on the hour. Make sense? So while we're taking the break, if you have other questions, you're welcome. I'm sorry, go ahead, Matt.
That will be great.
Okay, sounds good.
Excellent.
So in case I forget, let's make sure that, Matt, you can remind me that to make sure we take a break every hour, right? And stuff.
Perfect.
Yeah, sounds good.
We can do that.
Okay, so we'll reconvene at 30 minutes of the hour. And I'll fill up my water. Okay, let's go ahead and start. Thank you, Matt, for the timer. That is a good idea from the students. So let me go ahead and share my slides. Zoom, share screen. Okay. Perfect. And let me maximize the screen. Okay, good. We are now talking about power delivery network design, the key factors that we need to consider with doing so. Here is a schematic representation. So I just want to confirm, Matt, can you hear me?
Yes, we can hear you
Okay.
and see the screen.
Okay, wonderful. Thank you. So this is the second mini lecture, if you will, and here we are talking about power delivery networks. So this is a schematic. So you can see on the left-hand side, we have a voltage regulator that provides a input voltage, which is commonly represented as VCC in electrical design. And this is one, and here is another voltage regulator with another V input with VCC2. Now, one of the students had a question, or a couple of the students had a question about the color of the different lines coming into the circuit boards with the previous mini lecture that I had answered. And so this is an illustration of this, where here you can see there's an orange line and a green line, and here we have a purple line and a green line. So you could have a ground line and a power line, and these power lines are different from each other. So the power line you can see is going through all of these system blocks, and you can see here is the VCC load, which is the die, the logic part of the die, for instance. So whatever the functioning operational part of the die is. So that is one VCC, one input voltage. Here's another input voltage series of circuits on the same die with different load. Now, the reason why you would separate the two of these out is there are some chips that actually have two different voltages to different parts of the chip. That's unusual, but that's sometimes done. And in some cases, even otherwise, even if both of these voltages in are the same, you may want to isolate these two circuits to avoid crosstalk or cross-contamination. One part of the die may be less susceptible to issues if you have a power glitch, for instance, like a voltage spike or a voltage drop compared to another part. So you may use a more stringent voltage regulator for the more sensitive part of the circuit, and that's why you would separate these out. So here we've talked about the fact that you have a motherboard, then you have sockets that make connection to the motherboard, then you have the package, then you have the die making contact to the power to the package. So when you look at this physically, the voltage regulators are basically providing input to the power planes on the motherboard. And this is what I mentioned previously, where you can have a green, like a ground plane, which is basically metal. It can either be a metal sheet or it can be metal pattern metal layer. Then above this, we have the next layer of metal that's isolated from the other, where here either it's a sheet or alternatively it is thick lines, like so they're buses that carry power. So this will not be a solid sheet, but it'll be basically a pattern sheet that carries power from the outside to the inside and so on. And so the red is basically the sheet or the printed lines that are deriving power from VCC1 from the first voltage regulator. The purple sheet here is deriving power from the second voltage regulator, and that is built into the motherboard. Now we go to the socket. So you got all these sockets that are basically translating power from the motherboard. So from the motherboard to the package here, to the package is over here. So here you got the sockets, and the sockets have different colors. So they're using VSS for the ground plane in this case. And you can see that those are green. The red are the voltage regulator 1 power lines, and the purple are the voltage regulator 2 power lines. Power planes, power sockets going to the package, and in the package you've got these planes that again represent planes of metal in the package, and typically these planes would be patterned, so they'll actually be thick lines in one layer. So package power planes, this is built into the package, and then from here it goes to the die metal grid. So you got the interconnect metal in the die that has to talk to each of the transistors and the capacitors and the resistors that are built into the die. And those are typically a grid of lines like this. So here you have a red power line, a green power line. That's not right. The green is the ground line. Then you got the purple power line and a red power line, another purple power line in one plane. They're not talking to each other, at least they're not connected here. They're connected typically through devices. They go down to the die to devices. And all of these interconnect layers are higher above the devices. So that's the die metal grid. So the power delivery network, its purpose is to deliver power through the motherboard, through the sockets, through the package, to the die. And the ideal situation is you have good power efficiency and good signal integrity. Power efficiency is a function of, if you put in, pick a number, 60 watts of power into the die, you want all of that power, or as close to that power, that amount as is possible, to actually be used in the operating of the die rather than being lost in transmission losses because of heat the power being used up in heat dissipation with electrons moving through the wires anywhere in the motherboard, in the sockets, in the package, or in the die itself. That's power efficiency. Separate from this, you want signal integrity. So I've mentioned the fact that we have power lines coming in, but we also have signal lines coming in. Signal lines typically have less current flow than the power lines, and the signal lines have to be protected from variations in the power or variations in other signal lines as well. So you may be aware that there's a lot of parallel, like similarity between what we do with dice and human beings, the way human beings are designed. If you look at the design of human beings, you know that signals are transmitted in the human body via nerves, right? So the nerves act kind of like the electrical connections here. But you may also know that the nerve signals can crosstalk in certain cases. Now, in fully healthy human beings, the system is designed so that you do not have crosstalk between the nerves. So that's why when you taste something, you just get a taste and you don't get a flash of light or hear a sound. But there are some people, and there's a particular, I think it's called synesthesia or something of the sort, where there's some kind of a misbehavior. There's something wrong with the wiring in the person. So when you go to one nerve and another nerve like this, the nerve is surrounded by a insulating sheet, right, of proteins, basically. Now, in certain diseases, what happens is that protein sheet gets degraded. And now what can happen is a signal going down one nerve in the human body can talk to the signal in the next nerve. So people like this can sometimes, when they hear a sound, a particular frequency, they will see a particular color of light as well, purely because of that frequency, or they'll generate a certain taste, for instance. And vice versa. You can eat a certain food, and when you eat the certain food, you get a certain impression of a certain color or a certain sound. And that is an example where signals are cross-talking in the human nervous system. So the same kind of thing can happen with chips, where signal going down a signal line can actually be interfered with. There can be crosstalk between that and another signal line, and there's a lot of work that goes into avoiding that on chips. Okay, moving on. Key power delivery metrics. Voltage droops. A voltage droop is a voltage drop because of a current transient. In other words, if you suddenly ask the power supply to draw that you need a lot of current, what happens is the power supply is operating at a certain voltage, but if you pull up the current, you ask for a lot of current, the voltage supply is not able to provide that power in such a short period of time, so the voltage drops. So here is an illustration of this. On the y-axis here, we got voltage. On the x-axis, we have time in nanoseconds. And so this is a situation where the voltage, when you're not calling any power, when you're not calling any current from the source, is at point whatever 965 or whatever this number is, right? So let's call it 0.96. Now, when you suddenly like you switch on a bunch of devices on your chip, and so you draw a lot of current, what happens is there's a sudden demand on the voltage regulator or the voltage source. And this demand is for electrical energy. So you're suddenly drawing a lot of current, and the voltage regulator or the voltage source, whether it's a battery or a capacitor or whatever, takes a little time to respond. And because it takes a little bit of time to respond, what happens is When you draw a lot of current, there's a sudden spike down in the voltage, and that's called the first droop. Then what happens is the circuitry compensates by saying, oh, the voltage dropped below the level that we want, so it's going to pump more energy into the system. So you have a sudden spike up. So the spike down followed by spike up, followed by an oscillation like this. So this is the second voltage droop, then a third, and like this whole thing is called the third droop. And so when you're drawing current, you can see that the voltage that you are getting, so you're getting a current here. So with no current, you have a high voltage. But once you start drawing current, you see this kind of behavior. So the problem is any of these spikes, this lower spike, this higher spike, this oscillation here, any of these can create issues with your circuitry. Like, for instance, it can switch off, it can vary the timing of the signals that are propagating through your logic circuit, which will throw things off. So 1 + 1 will end up being 5, for instance, if you're not careful. So that needs to be corrected for. Moving on, another power delivery metric is the PDN. PDN is power delivery network. Impedance. This is the equivalent impedance. And I remember that we mentioned that the impedance is the resistance to alternating current. It's the impedance that is seen looking into the delivery network by the silicon die. So the silicon die is here and it's looking out to the voltage regulator and the power supply network to say, hey, I need power. So what is the impedance? So what you want to do is, we'll talk about this as we move to signal integrity, you need to match this impedance. So here between the die and the power delivery network, if you don't, you'll have signal reflections. So impedance measured here in milliohms on the y-axis versus frequency measured in megahertz. It turns out we have seen that impedance is a function of frequency. So like in the previous mini lecture. So you can see that impedance, the system, the chip behaves like a system that has a certain resonant frequency or a combination of resonant frequencies, because different devices on the chip behave differently at different frequencies. And that is true of the power delivery network as well. So as a result of this, you typically would end up with a low frequency resonant peak where some devices are responding at low frequencies, then another mid-frequency resonant peak where there are other devices that are responding at that frequency and they're responding stronger than at higher or lower frequencies. So that you can see is that at about whatever this number is, maybe about 2 megahertz. And then when we move up here, a high frequency resonant peak is occurring here with a higher impedance at about 100 megahertz. So depending on the frequency of the signals that are coming into your system, those signals are going to see a chip or a power delivery network that appears to have a different impedance. And that's something, again, that you have to, this is why when you're designing these chips, you design the chips to be the most efficient in operation at certain frequencies. So if you are clock rates, so if that's, there was a previous question in a previous, I think last week, about overclocking, turbocharging, turbo boosting, and so on. So there's a limited range in how much you can change the clock speed and still have efficient operation of the chip, because the fact that the chip is designed to work well at certain frequencies. So continuing on with power delivery metrics, Fmax is the maximum operating frequency of a microprocessor for a given voltage. So here's an illustration of some of the things that I've talked about, where Fmax is the maximum frequency in which the chip can do operations and still do them correctly. So here is an example of a 2.6 giga, reminder, giga is billion, so a billion cycles per second. So that is the clock rate. That's the clock rate that this chip, in this case, a Core 2 Duo, that means 2-core Intel chip, is being operated at. And when you operate it at that frequency, you end up correctly coming up with the correct answer, which is 2 + 2 = 4. However, if you try to overclock the chip, or for some reason the chip starts overclocking, instead of operating at 2.6, it starts operating at 2.7 gigahertz. All of a sudden, now what happens is the chips, that is the signals, the zeros and the ones that are traveling through the core logic, they start piling up. So one chip has, one signal has not, one number one, has not moved past a given device, a given gate, for instance, before the next one comes in. So as a result of this, you can end up with incorrect logic. And so you end up with answers like 2 + 2 = 9, which is wrong, of course. And that's why you have to be careful about operating. This is one reason why you have to be careful about operating the chip at the designed frequency. So components of a PDN, the power delivery network. So here's a very simplistic model of the network. So we have seen this schematic before, right? So you got the voltage regulators, you have the motherboard, the sockets, the package, and then the die on top. And then here's the load, right? This is the die metal grid. That's the interconnect grid, bringing power and signals to the devices. And here's the load on the chip, which is basically the devices. So this is represented electrically by this. So here is the platform DC to DC converter that's providing the voltage. So this is the Vout of the platform that's coming in to the motherboard. So the motherboard can be modeled as a resistor. So RMB is the motherboard resistor in series with a motherboard inductance. So the resistor resists the direct current flow of the electrons. The inductance resists a change in the current flowing. And this is in parallel, right? Parallel shunt with the effective series resistance of the motherboard, then the effective series inductance of the motherboard here, and a capacitance of the motherboard. So this is a very simple model of the motherboard. And that is attached to a simple model of the socket here, which is a resistance and an inductance in series. Then here is a simple representation, electrical representation. It's a model of the package with an effective resistance of the package, inductance of the package in series. And in here in parallel, we basically have the series resistance, the effective series resistance of the package, and then the inductance and a capacitance. And you see a similar model as we propagate through the system. Here's a die. So each of these are typically tested and modeled separately and then brought together. So somebody has to physically test these and determine the effective numbers here and then match it, calibrate it to the simulation. So in general, simulations by themselves are not very good. Without calibration, you have to calibrate it to the real world. So there's a lot of work that goes into calibrating models with the real world. And then once you have a calibrated model, you can then go ahead and use it for a new design, for instance, as long as the new design is not too different from the design where an actual physical motherboard was created and then tested to get these parameters. Similarly with the sockets and the package and the die. So the die is basically modeled as, this is the Vout with a shunt or a parallel resistor of the die, effective equivalent series resistance of the die, and a capacitance of the die. And over here you have the load, which is basically the logic parts of the die and so on. So the response of the PDN, power delivery network, to a current transient, we've already seen this, the voltage as a function of time, voltage droops oops, sorry. Trying to go back. Let's go back there. So we've seen this. Okay, we've seen this. We've also seen the schematic. So what happens here is when you have this first negative spike that happens within the first few nanoseconds, this spike is due to the loop that's marked omega-1, that's here. So the die is here, right next to the die is the package. So this combination of resistor, inductor, and capacitor creates a resonance that interacts with this drop, creating the first droop, right? Then the second voltage droop, which is a voltage drop, it's also called a droop in this context. And the third voltage droop, that's this, occurred due to the remaining resonant loops of omega-2 here and omega-3. So the impedance of these resonant loops, that's the effective impedance given all of these devices, determine the value of the droops. So if you want to control the value of the droops, you have to adjust these by adding in. Somebody had asked about how do you determine what capacitance value to add in? You do this kind of modeling and then calibration. And you basically adjust. So this tells you what happens if I add a resistor or an inductor or a capacitor wired in certain ways. And that will result in minimization of these. And so that's what you're trying to do. So each different motherboard design, each socket design, each package design, each die design will end up in a difference omega 1, 2, and 3, which means a different behavior like this. And so you literally have to go through this process of simulating it, creating a test system, checking, calibrating the simulation, going through this, and then changing the values, going through this a few times to get to the correct values that you want. So in the case of resonant circuits, so we implied that those circuits were resonant, they were resonating at certain frequencies. So this is the behavior of a resonant circuit where an RL circuit has an inductance and a resistance in series. So if you look at its impedance, Z, as a function of the frequency, at low frequencies, the resistance dominates. At high frequency, the inductance dominates. In the case of an RC circuit, that's a resistance capacitance circuit. So here's the resistance, there's the capacitor. What happens is the resistance is dominant at intermediate frequencies and the capacitance is dominant at lower frequencies. You look at a RLC circuit that has an inductor, a resistor, and a capacitor, in this case in series, the inductors behave like this. At a low frequency, the capacitance is dominating, like here. At the intermediate frequency, the resistance is dominant, like here. And at a high frequency, the inductance is dominant, like here. So the ideal power delivery design takes each of these separate components. So we talked about the fact that you've got the voltage regulator, which is modeled with an inductor, a resistor, and a voltage source. Then we have, this is BLK's bulk, that's the bulk silicon, inductance, resistance, capacitance. Then you got the motherboard, which is the, inductance, a resistance, and a capacitance. Then the package, inductance, resistance, capacitance, and then here we have the die itself modeled by an effective resistance, capacitance, and that's the load. So what happens is, as you look at the impedance as a function of frequency, so the effective impedance as seen by the load has behavior that looks like this. Depending on these values, you will end up with a resistive component here followed by a changing impedance where the inductance takes over. Whereas for the bulk, you have capacitance dropping, inductance due to capacitance drop, then resistance flat, then the you have the capacitive behavior, the inductive behavior of the bulk going up. Then here we have similar behavior, these trough-shaped behaviors for first the voltage regulator, then the bulk, then the motherboard, then the package, and then the die. And so by looking at this, depending on the frequency, we have to control the impedance for whatever frequency you're going to try to operate the die at. So when you add all of these things together, that's what the circuit looks like. There's the voltage source, the voltage regulator, here's the bulk silicon, here's the motherboard, here's the package, here's the die, and all of these things effectively all kind of combined together into what is seen by the load, which is basically the die logic portions and so on, or whatever functional portions you have on the die. So the result of all of this is what we have seen before. Impedance as a function of frequency. We see the impedance has a resonant peak here, and the brown areas correspond to these two combinations of the bulk silicon and the motherboard. And then you have the and then the green areas are the socket, the package, and the die. They're combined to give you this resonance. So there's a lot of work that goes into this. So why do we care about voltage group? For the same reason we mentioned previously. 2.5 gigahertz, the chip works fine. Increases to 2.6 gigahertz, which is the maximum frequency that you can operate this chip at, it still works. 2 plus 2 equals 4. Push it to 2.7 gigahertz, all of a sudden now the signals run into each other. And so the zeros and the ones start running into each other, and you end up with incorrect calculations. And that's why, so what you do is you try to find a plateau and say, okay, the maximum frequency that you're allowed to operate this chip at is, in this case, 2.6 gigahertz. So here's how we look at the impact of the voltage group on the maximum frequency of operation of the chip. Fmax in gigahertz, it's the frequency on the y-axis. Along the x-axis is the voltage that you're putting into the system. It turns out that the frequency of the system changes as a function of voltage. So if you operate, so what we do is there is a range in which we permit the chip to operate of voltages. So let's say that your target voltage is 1.2 volts for your chip, but together with the groups at times, let's say that we allow it to go down to 1.0 or we allow it to spike to 1.3. So this is the green is the operating range. So that is the tolerance. TOL is tolerance resulting from noise in the power supply, for instance. And so here, if we say the tolerance is plus or minus 100 millivolts, the range of voltage where you can operate the chip is the green area. So as you increase the operating voltage, the operating frequency increases. So the frequency at the bottom end of this is 3.7 gigahertz. And so that is what the chip is rated at as the Fmax. In reality, if you're operating here, the chip will actually be operating at a higher speed, but nobody complains if the chip operates at the speed higher than what you said was its max. However, if you said this is the rated frequency, and because of noise, you're actually operating at a lower number, you'll find your chip is not performing and the company will get into trouble with the customers. Now, if the voltage goes beyond this range, then what happens is you end up in this scenario where even though the frequency is increasing a bit, but not very fast, it's plateauing, you end up with reliability issues like the 2 plus 2 equals 9 instead of 2 plus 2 equals 4. So if you were to make you engineer your power supply and so on better so that the noise tolerance is smaller, so instead of plus or minus 100 millivolts, you engineer your capacitors and inductances and resistances in such a way that the noise that you're tolerating in the system is plus or minus 50 millivolts instead of 100 millivolts. Now the green band becomes tighter. Your normal VCC nominal can operate at 1.25 volts instead of 1.2 volts on the left. And as a result of this, the reported max frequency goes up to 4 gigahertz. So this is linked to your design. If you design tighter, what happens is you can operate with a higher frequency than here, which means your chip is higher performance, which means you can sell it at a higher price for high performance applications. So summary of this, the performance of a power delivery network can be entirely described by the effective impedance seen by the load as a function of frequency, and that's called the PDN, or power delivery network impedance. The variation in the impedance that's seen in the frequency domain, that's impedance as a function of frequency, manifests itself as a voltage fluctuation with time. So the voltage groups when the circuit switches. When the circuit switches from one state to another state, it draws more current. When it draws more current, the voltage drops. When the voltage drops, then you can end up with the oscillation that we talked about in the impedance and in the voltage. And that can then result in the chip not functioning properly. 2 plus 2 equals 4, 4, 4, and then all of a sudden it switches to 2 plus 2 equals 9. And you do not want to go there. So voltage groups affect the CPU performance by affecting the operating frequency at which you can operate the chip. And you all know that you want chips that can operate faster in order to get things done faster, right? So critical thinking, again, for you to think about how does the structure of a power delivery network within a semiconductor package impact its ability to efficiently deliver power to all components? And what design considerations must be taken to optimize the performance of the system? And we talked about many of these elements in this presentation so far. Second question, in what ways do the interconnects and materials used in a PDN influence its overall function? So if the interconnect resistance is higher, you have, right, the effective resistance changes, which changes the behavior of the voltage group and so on and so on. How might different design choices affect the power integrity, that is the stability of the power, and signal quality, that is the non-degradation of the signals in high-performance semiconductor systems? Third question, how would variations in the design of a PDN within a semiconductor package affect the system's ability to handle dynamic power demands. Basically, when you're switching from one state to another state and you're drawing more power, then the voltage drops. So how do you handle this? What would variations in the design, what would it do? What strategies can you employ to ensure reliable power delivery under varying load conditions? So all of these are, we've given you enough data to be able to think about these things and write down some responses. And you can also research more advanced applications of these. Okay, I've stopped sharing that. I'm going to jump to the third micro badge. And I'm sorry, the third micro lecture or mini lecture. Okay, so number 3. Okay, there we are. So here, I'm going to go ahead and maximize the screen.
Dr. Theodore, looks like we have a question from
Okay.
Jose.
Yep.
Yeah, Professor, I remember when I saw the last computer that they opened to myself, the desktop computer, it had like a power source. It's where the electricity comes first before going to the motherboard.
Okay.
Do the motherboard or that power source has a relay or something that will detect the instability of electricity in voltage, and it will cut the energy to protect the microprocessors, or the motherboard doesn't come with that? I mean, is there a
That's a good,
device?
yes, that's a good point. I would say that it depends on the design of that, of the motherboard and of the power supply. So the power supply, typically, as you may be aware, you have an external power supply that takes 120, like whatever you have in where you are.
120.5 volts.
You have 120. Okay. So you'll take the 120 and convert it. So you have 120 AC, alternating current, that's coming from the wall, right? Wall socket. So the power supply, you typically have an external power supply that converts that AC into a DC, direct current, and a lower number, which could be like 20 volts, depending on the laptop, right? And or it could be 12 volts or 15 volts, whatever number your laptop is specified at. Now that power supply cleans up a lot of the power, but it's not perfect. So that power then comes into the power unit on your laptop, and that laptop has additional electronics to clean up the power further. Now, the actual voltage that is used by most devices is not 20 volts. So if you have an external power supply that's feeding 20 volts, or pick a number, right? If it's 15 volts, like let me look at mine. Actually, it's kind of small. I think in the past when I looked at them, they said about 20 volts. So 3, yeah, it says my power supply says 20 volts. So if it is supplying 20 volts to my laptop, the actual voltage that the device needs is much lower. The device can be operating at as low as like 1.2 volts, right?
Very low.
Like for switching and so on, or it could be higher, it could be 3 volts, but it's typically never as high as 20 volts, unless you're talking about power devices, which are typically not, rarely used in a laptop, right? So like they would be used in cell phone towers, for instance, where you have to pump a lot of power to broadcast signals. So what happens is you have to have circuitry that will downshift the 20 volts that's coming in down to the voltage numbers that are needed by different parts of the circuit, which could be all the same voltage, or it could be different numbers. It could be 5 volts in one place, 3 volts in another place, 1.5 volts in another place. Now, as part of this, it is an extremely good idea, what you mentioned, to ensure that there is some kind of a relay or something like that that will switch the laptop off, or will alternately shunt the power to the battery, the power being supplied to the chips, to the logic, to the battery, rather than having it come in if there is a power surge and there's a spike that comes in. Now, I expect that all laptops have this, but I don't know the answer to the question, does every single laptop have this? I would think that it should. I know that some do. Right?
Okay.
But that's a good question. And if it doesn't, it's a good idea to have one, right?
Thank you.
So okay, so yeah, let's go ahead and move to the next presentation. And I'm not sure if you can see the presentation. Let me check. Actually, yeah, Matt, are you able to see my presentation?
No, not right now.
No. Okay, so I need to go and share screen. Thank you for confirming. Okay, I'm going to go ahead and shut this window, make sure that I have the correct presentation up. Escape. Okay, so I should be at the third. So let's go ahead, and that's the correct one. Go share it. Okay, so it's being shared. Now I'll maximize my screen. Okay,
There
perfect.
we go.
Okay, excellent. And maximize the screen. Okay, great. Now we're talking about advanced power delivery schemes. And here in this particular slide, we're looking at the scaling trends for advanced power delivery. So the classical scheme, in previous lectures, we talked about Moore's law, where the transistor count was going up. It was doubling approximately every 18 months to begin with, and every 2 years, something of that sort, right? So this plot is on the y-axis is basically a logarithmic scale. On the x-axis is the year, and this had moved up to 2005 when people were looking at single cores, which basically a single core is basically like a single chip that does the logic operation. And so any operation that you're asking the computer to do, it's going through that single chip. Multi-core is the equivalent of having, instead of having just one mother microprocessor, you're having two microprocessors, three microprocessors, sorry, 1, 2, 4, 8, 16 microprocessors, for instance, that are built into either multiple microprocessors on one package, or you're building multiple microprocessors into one die. So either of that is an alternative. So the green line basically here is looking at the transistor count, the total number of transistors in thousands. And you can see it's pretty linear on a logarithmic scale as we go as a function of time. However, there are problems with putting more and more transistors onto a single chip, and also difficulty with putting that into a single processor. And that's why we have moved to multiple cores. In the past, the industry as a whole was increasing the performance of the chips by increasing the transistor count. So as the green line went up, you can see the red frequency in megahertz was going up kind of linearly as well, together with this on a log scale. But after a while, you can see that we are having difficulty in getting the frequency to go up. It's kind of plateaued, right? We've reached a limit of how fast the individual chips are able to get things done. And in part, we are limited by material constraints, like silicon dioxide, and so on. And in part, we are constrained by the fact that we're not able to make the devices much smaller than they already are. So we are pushing down to 1.4 nanometers, but the device physics ends up being very different in the quantum realm compared to the regular electronic device realm. So for various reasons like that, we're not able to push the frequency higher. So in order to increase the frequency, the overall operation of the chip, we're being forced to go to multi-cores, which is multiple processors, microprocessors, either on a chip or in a package. And so the core count up to here was at 1, right? Up to 2005 was 1, and then it jumped to 2, and then you can see that gradually the number of cores are increasing. So at the high performance, this is making the point that the cores could be as many as 100 cores in the high performance servers and supercomputers and so on, right? I mean, typically a consumer laptop may have 4 cores, or I'm checking to see if mine says, I know that I have a multi-core laptop, but I don't see how many cores it is. Okay, it could be like 4 cores or something like that. Moving to the next slide. So there are power delivery challenges as we go to multiple cores. So here we're looking at a power rail is basically the bus. It's like a fat wire, like metal line that's bringing power, current, and voltage, electrical energy to the chip. So you have multiple rails to feed as the chips become more complex and they become more like bigger, and the number of chips increases. You need to have more of these power lines bringing in power. So in client power lanes, so client laptop would be like the laptop or a desktop that you use at home. The server, as you know, is typically a centralized computer that's more powerful than your client that basically can feed information to multiple clients, to you and to another student and another student and so on. So if you look at the rail count, power lines coming in as a function of year, you can see that the client power rails, the numbers are increasing to, in this case, more than 20, whereas server, the power rails are going up to 70 to 80 rails for a given server, for instance. Okay, I need to move my Zoom notification out of the way. So as the power rails, that's one thing that's happening. The number of power rails has been scaling up with the core count, and the overall power levels have also been going up in the high power segments of the processing areas. So here we see on the y-axis, we see thermal design power. That is the amount of power that you expect the chip to generate at like peak operation. And as a function of year, you can see, and this data is updated up to 2021, but projected for 2024, which is where we are. A mobile phone, for instance, the power is pretty low because your phone cannot handle much power. A desktop, you can see, has power in this range in the order of about 100 watts. High power central processing unit, that's the gray numbers here, is increasing to about ballpark of about 300 watts, but projected to go higher. And the high power graphics processing units, these are, as you know, they are chips that are used specifically for image processing, and they are much more powerful typically than a central processing unit because images have the highest density of data of things we do. Videos, of course, have higher data density. So the data density in an image is much higher than the data to process one image is much higher than for you to add up any numbers that you do in an Excel spreadsheet, for instance. So the GPUs, the graphics process units, tend to be more powerful. They have more rails. They have more power that's being dissipated. So you can see that now we are talking about 500, 600 watts targeted to go higher. Now, this is the reason why cooling of these devices becomes very important, because if you don't, this is a lot of power that's being created in a very small area because the chips are pretty small. At the most, maybe 1 inch, 1.5 inches by 1.5 inches. So the amount of power that you're generating is very high, which can melt the chip, or it can create many issues that I've talked about in previous lectures. So you have to get the power out. So that's a very significant challenge. So here, one of the methods for efficient power delivery is an integrated voltage regulator. So an integrated voltage regulator, in this case, so here's the platform converter and here's the equivalent circuit. Now you end up with multiple integrated voltage regulators that are producing on die DC to DC conversion, taking in a certain input voltage and giving you a different output voltage. So we talked about a laptop. You could have 20 volts coming in here and getting converted to 5 volts for part of the circuit, 3 volts for part of the circuit, 1.25 volts for part of the circuit. So you got multiple of these regulators, and they are actually built into the die. So they are called integrated because they integrated into the die, typically. One of the advanced methods of doing, so one advanced method is to go from on die or on package voltage regulators, you're going on to on die voltage regulators. That's what I talked about. Instead of having the voltage regulator on the motherboard or in the package, now you put it onto the die. That's one option. Another option is using power gates. And so a key component in a power gate is basically, it's a power FET, field effect transistor, that is able to handle high power. It can switch high power, and you build that into either the die, the chip, the logic chip, or you build it onto an adjacent chip that's going to provide power to the logic chip. So in this case, as a voltage, it behaves like a switch to give you, so 20 volts in can give you 5 volts out, or some number like that, right? So this is a schematic here. So here is an example of this where you have a multi-core module. You have basically power coming in. So here's a cache, and you have power that's going to these different cores. So here's core 0, which is the primary core. And in this case, it's on. So it's an active core. So the power gate, so this is the power gate here. This power gate is on, and so it's sending power to this core. Then what you can do in advanced power delivery systems, instead of always having all of the cores powered, anytime this core is not needed, you switch it off. So the power is off here, the gate is off, here the gate is off, here the gate is off. So all of the green cores, that's green core 1, 2, 3, they're all off. So they're not consuming power. You're consuming power only when you're using the core. So in the case of multi-core systems, for normal operation, you may use one core. For slightly more powerful operation, you can use a second core. As you need more and more power, depending on what you're doing with your laptop or server, you can switch on more cores by doing this. So power gates are used to turn off the power to inactive circuits like these cores to minimize their leakage power consumption. This is easily implemented through power FETs, power field effect transistors, to turn off the inactive cores. In this case, there's no voltage regulation or intermediate voltages that this chip is being exposed to as a result of the switching. Another way of handling this, or another form of advanced power delivery, is low dropout LDO regulators. And here's a schematic, like where you have power FETs and an error amplifier here. So there's a voltage in, then you have a FET, and then the voltage out with a feedback circuit through an error amplifier. That the error amplifier basically looks at a reference voltage, and you can wire it. If you do it correctly, what the error amplifier will do is it feeds a signal to the power amplifier, the FET here, to the gate, that will enable you to control the voltage out to match the voltage, the reference voltage. So if you have a high current draw that would tend to drop the output voltage, what you're doing is you're drawing energy from the input part of the circuit and using this as the intelligence to match the out to the reference. So that's how you keep the voltage stable in this case. So a low dropout regulator is named because the dropout voltage, which is the minimum difference between the input and the output voltage. In other words, these kinds of devices, regulators, are intended to keep the voltage, the output voltage, kind of similar, very close to the input voltage, even if there is a sudden draw. So they're basically DC. These LDO voltage regulators are DC linear voltage regulators that maintain the output voltage. That's this, when the input and the output voltages are close. And what it maintains this by comparing the difference between the voltage output and the voltage reference. This is easily implemented in silicon, has low noise because there's no switching that's actually taking place, but it's restricted to low power rails due to poor efficiency. So dropout voltage, a smaller dropout voltage indicates a more power efficient system, and most LDOs, that is low dropout regulators, have a dropout voltage between 70 millivolts and 500 millivolts. That is, the input and the output voltage have to be within this tight range. So continuing with this, the input voltage range, LDOs can be used in devices with a wide input voltage range, such as battery-powered applications. The LDO operates by comparing the regulator output, that's this number, the Vout, to a reference voltage here, this reference voltage, via a feedback loop. And the LDOs are typically used in post-regulation to provide a constant voltage, output voltage, and noise filtering. So if there is a sudden change in the input voltage, what this does is it tries to minimize the effect of a change in the input voltage on the output voltage because it's comparing it to a reference voltage. So the error amplifier that's used here, now how does that work? The error amplifier is an electronic device that responds to the difference between a reference signal and an input signal. So in this case, it's basically operating, so it's getting the input here, it's looking at the output here, and if there is a difference here, it changes the output here with the feedback loop. So the error amplifier adjusts the output driver on resistance to maintain the output voltage, that's this. If the voltage is higher than a desired value, the desired value is programmed in here, the error amplifier increases the on resistance. If the voltage is lower than if this voltage turns out to be lower than the reference, then it decreases the on resistance, which causes the voltage to adjust to keep the stable to match the reference voltage. So buck regulators, I think Professor Alford briefly mentioned buck regulators when I looked at the slides in yesterday. But basically, a buck regulator has this kind of a circuit where you got the input, a transistor, another transistor, an inductance, a capacitance, the voltage out here, a reference voltage, and the error amplifier here. So the key components here are the power FETs, the inductor, the capacitor, and the controller. So they are switch mode, step down DC converters. They're more expensive and difficult to integrate. They're typically used for high power rails to take advantage of the high efficiency because you want to minimize any power loss. And they offer granular control of the output voltage, which basically means you can control this at different levels with good precision. So the buck regulator is named after the inductor. That's this. In the device, which bucks or opposes any changes in the input voltage. The term buck also means the resistor reduce, allotrates with the opposite, which is a boost regulator. So the buck regulator, it's also known as a step-down converter. It's a type of DC to DC converter. Produces a lower output voltage. So this output voltage in this case is lower than the input. So you could put in 20 volts here, for instance, and get out 5 volts, or put in 5 volts and get out 3 volts. It's a popular topology, that is the circuit design in power electronics, and it's used in applications including USB, battery chargers, solar chargers. Another advanced way of handling power delivery is a fully integrated voltage regulator. Here, an MBVR is a motherboard voltage regulator, and so here the regulator is actually on the motherboard, it's not on the die. Whereas FIVR, you can actually put this onto the die. So the FIVR, the fully integrated regulator, was first introduced in the 4th generation Intel core processor. The high frequency, so this can operate at high frequency, enabled the use of air core inductors as the energy storage component. We'll see that on the next slide. So the motherboard regulator basically acts like this. Here's the platform, here's the package, here's the die, and there's a distance between here and here. Whereas when you integrate this on the die, you got the die and you got the components of the FIVR that's actually integrated on the die. And here's all the chip circuitry and the controller. So platform impact of the motherboard versus the fully integrated. So here we have a bunch of different kinds of voltage regulator. So looking at this, VR stands for voltage regulator. MBVR we've already seen as the motherboard voltage regulator. FIVR is fully integrated on the die. PLL VR, you can see. So I have mentioned previously that you have different voltages coming to the chip. So here is the actual core processor. So the PLL VR gives you 1.8 volts, and that's a phase-locked loop voltage regulator. The core voltage regulator gives you 0 to 1.2 volts. That's the core, is the VR for the core, chip core, the logic parts, and so on. IOVR here gives you 1 volt, and that's basically for input-output. The GFX VR, 0 to 1.2 volts, is basically for graphics processing. SAVR is the system agent VR, which is typically for RAM, for built-in memory, random access memory. So this is in the case of the motherboard voltage regulator. In the fully integrated regulator, you have a bunch of these different FIVRs. So they're smaller, but they handle specific parts of the chip. So here's an SAVR that's leading to logic. VCCIO, that's the input voltage FIVR. They got a different one here. Then, so VCCIO is the voltage for the input-output pins of the CPU. OPIO, so there's a bunch of core regulators providing separate voltage power to different parts of the logic in the circuit to separate out so they don't have crosstalk between misbehavior of the power in one part of the circuit compared to another part of the circuit. And also, by having part of the logic draw on one FIVR voltage regulator, you don't have to have that regulator handle as much power as if you had one voltage regulator for all of the logic. So here you have 2 graphics voltage regulators. You have the OPIO is the optical input output for optical signals. EDRAM is embedded dynamic RAM. So you have a separate, fully integrated voltage regulator that's producing power, providing power for the logic. So you can see that there's an input voltage regulator providing input that's then split up into all of these, and you can use different voltages as needed. Summary: scaling ensured exponential performance growth without increasing power density. So scaling was basically where you make the devices smaller and smaller, so you're able to put more and more of the devices on a given chip. So that enabled performance growth to go up exponentially, right? Without increasing the power density until about the mid-2000s, about 2005. But then after that, we ended up having to increase the number of power rails, the microprocessor power levels, and there was a need for new power delivery solutions because of those challenges. And we saw several new advanced methods that are being used to address these. So the development of high efficiency, high density, high voltage, integrated voltage regulators has been critical to meet the requirements for the current high performance microprocessors, but also as we go into the future where the number of cores will go up, the power will go up. Okay, so here critical thinking for you to consider: how do advanced power delivery schemes differ from traditional methods in terms of efficiency and scalability in supporting high-performance semiconductor devices? What challenges do these advanced schemes face in packaging? How do these schemes contribute to improving energy efficiency and minimizing power loss? In what ways could the implementation of these schemes influence the overall design of semiconductor systems? We've already seen some changes where these voltage regulators are being moved off of the motherboard or the package. So initially they were moved from the motherboard to the chip. Now they're being moved from the motherboard, from the chip to the package. They went from the motherboard to the package, and now they're moving from the package to the chip. So that's one example, right? And how might future technological advances further evolve these schemes? Things for you to talk about or consider. Okay, so I'm going to close this third micro. Okay, so I'm looking, that is a micro lecture that I just closed. What is a power rail? I'll handle that question. The power rail it's called a rail because I think historically, if you looked at electric trains in real world transportation, there were many electric trains. In some countries, the electric trains had their power from overhead lines, right? So the electric train has an engine that has this electrical system that contacts power lines that are above the electric train, and that transmit the electric power to the electric train for it to be able to move. But in other countries, what happened is that instead of having these lines above, you have a third rail. You have two rails that the train runs on with the wheels, and between those two rails, you have a third rail, which has high power. And what happens is now there's a connection between the electric train and that rail, rails that gives the train power. So very likely that's where the term came from. So the power rail is basically a fat line. It's like an electrical line, like a metal line, like a copper line or something, that's thicker and wider than the normal interconnect lines that you see on a chip. So these lines are called power lines, the rails, because they're bringing in like 100 watts worth of power or up to 600 watts. The combination of these rails are bringing that amount to the chip. So that's why it's called a power rail. Okay, so let's go ahead and look at the final micro lecture or mini lecture for today. And then we can...
Dr. Theda, we are coming up on the hour. If you want to take a break now, or if you want to push through, I know we still have the activity afterward too.
Yes. So I think I was supposed to go until 7:45, right?
Yes, that's the schedule.
Okay, so how about I go through this lecture, then we'll take the break, and then we can start the activity. Is it okay?
Perfect. Let's do it.
Perfect. Thank you for bringing it to my attention, because I'm completely capable of forgetting. Okay, so advanced power technology. Let me make sure that it's the fourth one. Yes, it is the fourth. lecture, and we go here to share screen. Share the screen. Okay, it showed up, and I will maximize the screen. Okay, let me see how many slides there are. Okay, 18 slides. Okay, so now I'm going to maximize the screen. Okay, great. And get a little bit of water. Okay, we're now talking about advanced technologies for power delivery. It's an extension of what we previously spoke about. So here we've already seen this slide. The left-hand side, thermal design power versus year, we saw that it's going up significantly. So at the bottom in yellow, as the power levels continue to go up, it's important to deliver high voltage integrated voltage regulators to keep the routing losses manageable. So routing losses are basically, so when we've got the power coming through these fat lines, right, to the chip, what happens is there's resistance in these lines. And so the resistance in these lines is pushing back against the electrons that are trying to move to bring in the power. And because of that, the lines are losing power. So it turns out that to get a couple, you may be aware of the fact that voltage multiplied by current gives you the electrical power. So if you have a low voltage for a given amount of electrical power, if you have a low voltage, you have to have a high current. And resistance opposes that current. So one solution is, instead of having a low voltage, increase the voltage for the power delivery. That means the current is lower, which means the resistive loss is lower. So that's one reasoning that leads to the need for high voltage integrated voltage regulators. So here are the routing losses, the fraction of the output power that's lost. And you can see that the losses can go up to 20% in the case of this red line here is for an input voltage of 0.8 volts. For a given amount of power that's coming into the system, if you have a low voltage, you need a high current. If you have a high current, that high current is resisted by the resistance. And that's why this red line so steeply goes up as you increase the output power. So here, by the time you get to 200 watts of output power, you can see that 16% of that has been wasted, thrown away. If you increase the input voltage from 0.8 down to increase it to 1.8 volts, you can see that the rate of increase is lower, 2.7, 5 volts, and 12 volts. So if the input power is 12 volts, you can see the green line here, the losses are less than 1%, up to 1,000 volts. 1,000 watts of power. So this is the driving force for us to increase the voltage of the power handling coming into the chip. So here is an example. So this is an advanced technology. It's an example of a high voltage integrated voltage regulator configuration. HV stands for high voltage, IVR we've already seen, integrated voltage regulator. VR chip is a voltage regulator chip. So in this particular case, here is the CPU, the central processing unit. There are the solder balls making contact to the package. And beneath this, you can see the capacitors. These are the land side capacitors that are right as close as we can get them to the CPU, but on the other side of the package. Here is an inductor on the package, and here is the voltage regulator chip, and here is a capacitor. So the VR chip here is basically handling higher voltage than in some of the previous designs. So the integrated VR can be made in a variety of ways. In this case, placing the inductor, that's this, and the capacitive elements, that's here and here, on the board, in the silicon, or embedded in the package, for instance. Here's another configuration where they have embedded, instead of having the inductor sitting on the side, like the previous slide, now the inductor is embedded inside the package. So here's the CPU, the central processing unit, the chip. Here are the the land side capacitors near the chip, and now we embed an inductor inside the package. And above that is the VR, that is the voltage regulator chip. So that's a second configuration. Another configuration is this, where here we can see that the inductor is a silicon inductor that's built into the voltage regulator chip instead of having to put it in the package or laterally. So by doing these kinds of things, we're able to make the package smaller, because inductors, onboard inductors and capacitors tend to be large compared to the die, which makes the size bigger. So here's an example. This is the third configuration. A fourth configuration is here, where we are putting the voltage regulator circuits on the CPU itself instead of having it on a separate chip. So here's the central processing unit, then voltage regulator, central processing unit, voltage regulator. Now we have a LAN side capacitor here and a die side capacitor on the package. Similarly here, LAN side capacitor. And now we've put the inductors directly beneath the chip. So this is a different configuration. So all these are attempts to be able to bring in a higher voltage to the chip, but at the same time to have the regulator circuitry near the chip to downshift from the high voltage to a lower voltage to give it where needed on the chip. And here's yet another configuration where in this case, we have the inductor that's embedded in the package instead of putting it beneath the chip, beneath the package at the bottom side of the package. Whereas we're doing the same here, we have the capacitors beneath the package. So that's the LAN side capacitors. And here we have the die side capacitors. And here we got the VR voltage regulator circuit that's built into the CPU chip. So typically the integrated voltage regulator design targets, they are targeting an input voltage of 5 volts, output voltage of 0.6 to 1.2 volts that goes to the devices like the transistors. Current density is greater than 10 amperes per square millimeter of chip. Target efficiency greater than 90%, the higher the better. Switching frequency typically 10 to 25 megahertz, million cycles per second. So the ingredients, the technologies needed to do these include device technologies to enable these, the high voltage integration, magnetic inductors, advanced decoupling solutions, and advanced packaging technology. Because now we're handling comparatively high voltages over very small distances. So the existing technologies, this is a fiber, which is basically a fully integrated voltage regulator. And this is using ACI, which is air core inductors. We have already seen this slide where on the die, so here the gray area is the die, we are integrating the air core inductors here with the die itself and building this into the package, which is then put on the platform. So here is an image showing the air core inductors. So in this case, you can see these posts. The yellow top, these are connection to the MOSFETs, metal oxide semiconductor field effect transistor. So it's basically a transistor. And the inductor, okay, and then the blue dot the posts with the blue dots are those that are connecting to the Vout, the output voltage. So you have inductors here. Basically, you have these, it's like a coil of wire. And then the current, when the voltage sends a current through this inductor, when there is a change in this current, it creates a magnetic field, right? So first of all, if there is a current, you'll generate a magnetic field. That magnetic field stores a certain amount of magnetic energy here. If you try to change the current, this magnetic energy will compensate for the change in current to resist the change in current. So basically, the bottom line with this is the inductor stores magnetic energy, which is translated into current flow if the current drops below some number. So that's what the inductor is. So here's the physical configuration of the inductor that you can build into the chip or into a package. And it's air core, which basically means that inside the core, it's just air. There is no dielectric that's put in here. And so here is a chip that shows these the circuit configurations. And so my guess is that these are the capacitors and these would be the inductors that we are seeing here, right? That loop thing. So fully integrated voltage regulator that, like we talked about on one of the Intel chips, relies on air core inductors and MIM capacitors. We talked about MIM capacitors, metal insulator, metal capacitors. The air core inductors in this case are designed in the package. The MIM capacitor consists of parallel plates of metal separated by a thin dielectric. So it can be silicon oxide or hafnium oxide or whatever, and it's designed in the silicon on the die. So here is the schematic we saw previously and the image of the physical configuration of the inductors. And here is a top-down view of the die showing the inductors and capacitors. So more advanced inductors are coaxial, MIL, which is metal insulator, and L stands for the inductance. So here is an example where we use a magnetic material in the inductor design, and this helps to improve the inductance depending on the magnetic material. So you can see different phases and different inductors going with that. So here, so the coax inductor basically has metal on top, magnetic material, dielectric layer on the outside, or vice versa. You can put the magnetic material outside here, then like a interface layer and the either an air core, or you can have a dielectric core here, and that creates the inductor here. And you have different ones of these with different physical configurations for different inductance values that are linked to different parts of the circuit. That's what the different colors mean. So here is a cross section of the same thing. So we saw this schematic on the right-hand side, the product on the previous slide. And now we're looking at a cross section through this to understand what it looks like. So here is a cross section. Here's the concept, which is basically drawn on somebody's computer. And here is the prototype that is physically made. So you can see in the prototype, as well as in the schematic that is drawn on a computer, there's a magnetic material here. There's a plated through hole via. So the through hole via is in this area. And then you have a dielectric core that is here. So you've got magnetic material, the core, which is made of a dielectric magnetic material, and then a via, right? That is the hole that's made through. And you can fill that with an insulating material if you wish. Or you might prefer to do that. So this, because you're using a magnetic material, it improves the inductance, which means that now you can make the inductors smaller and you can build them into the chip instead of having these huge inductors that are sitting outside the chip that makes your package larger. So another step is advanced capacitors, something called super MIM. Again, super as in super, and MIM as in metal, insulator, metal. So super MIM capacitor. So here is a structure where this is integrated on the silicon chip. So the silicon chip is down here. So you got the die. So this is silicon down here, the die, and then you have the transistors and so on. And above this, you got the interconnect layers. So the golden lines, the squares are basically lines that are coming out of that plane, which typically copper lines or something of that sort, where signals or power is being brought down here. You can see there's a device, there's a metal connection going down here, right? Ultimately to the devices. Now, the longer lines here can be a line that's going parallel to this face, parallel. And then you can see these vias, right, that are connecting upwards until we get to, you can build the super MIM capacitor on any of these layers up here, right? So this could be a super MIM capacitor connected down to another capacitor and so on, or this could be another capacitor, so forth, just as an example. Now, in this area, there's a 5x increase in capacitance. So 5 times increase in the capacitance by using the super MIM structure. So if you look at one of these, here is like a side view of this. And if you look at the side of this, you can see there's a series of layers with different metal layers. The golden layer is a metal layer. The dark layer in between is a dielectric layer. And historically, you would use something like silicon dioxide, SiO2, but you can now use different high dielectric constant materials. Each of these just a few angstroms thick that are stacked in a repeating structure, what's called a superlattice, where you have metal, dielectric, metal, dielectric, metal, dielectric. So this is a schematic, and this is a cross-section that we have seen before that shows a metal layer, this dielectric layer, like hafnium oxide, metal layer, like copper, hafnium oxide, copper, and beneath this is SiO2, for instance. Another example of advanced technologies that are being implemented are advanced transistor technologies. So in this case, this is called an E-mode high dielectric constant gallium nitride transistor. So this is a schematic showing a silicon transistor. We got a silicon, I'm sorry, it's not a silicon transistor, it's a gallium nitride transistor on top of silicon. So this is 111 oriented silicon, a buffer layer, which is typically like some kind of an oxide or something like that. Or it could be, there are other buffer layers that are used as well. Then gallium nitride, here's the N+ side of the device. Like, so there's a contact coming here, and you've got the gate, and here you got the channel. So you've got electrons that come here, and when this gate is switched on by applying a voltage here, this channel, what's called LG, would stand for length of the gate, switches on, and now current is able to go from the left side to the right side of this device. That's on silicon. So silicon buffer layer, which is, some of the buffer layers are proprietary to different companies, then gallium nitride on top. So here is a transmission electron micrograph of a structure like this that shows the gallium nitride. That's this yellow layer here. Then here's the gate region. And the white region here, first of all, shows that the gate is about 29 nanometers, which is pretty small. Then there is a high K dielectric here, and then the gate coming down here. And you can have contact to the source and the drain by an N+ layer going under here. So this is an example of a low voltage gallium nitride transistor, which is useful for high voltage applications because silicon transistors that are this small cannot sustain the high voltages that we're using. For the same device, if it's made with silicon, it would only operate at a much lower voltage. Whereas the gallium nitride is able to handle the higher voltage without breaking down. Another technology that's being looked at for advanced applications of something called power vias, where in the conventional method, you have your devices down here, and then all of these are dielectric and interconnect layers coming down to the devices. And all this is silicon, and you're not using the silicon for anything other than the transistor layer and capacitors and resistors down there, and also for support. But in the power vias, what we're doing is we're now making holes in the silicon beneath, right? So actually what's happening is the thin gray layer, so here you see the gray silicon is thick. What you do is you thin this silicon down to a much thinner. So this layer in most wafers could be 400 microns, which is almost half a millimeter. So what you have to do is you thin this down. You could thin this down to 100 microns or 50 microns. People are trying to push it thinner and thinner. And then what you do is you have metal lines that are coming down through these, the blue are dielectric like SiO2, silicon dioxide, and the gold, brown, whatever, could be copper layers coming down to a through via. This is called a power via. That is a hole that's etched in the silicon that takes power to the back of the transistor, to the backside. So these are backside interconnects and power routing. And this makes it possible to bring the power closer to the silicon instead of having to take it through many, many layers and a lot of distance with high resistance. So that's being explored. So in summary, high voltage integrated voltage regulators are needed to keep the routing losses manageable. Because we said, as the amount of power that we need to put into the device goes higher and higher, we are finding that we need to operate at higher voltages. But higher voltages tend to break down small silicon transistors. And so we have to look at other alternatives. So here we describe high performance integrated voltage regulators at the current stage and things that are being looked at, like going to gallium nitride instead of silicon, and for the transistors going into power vias, and also integrating MIM capacitors into the silicon and also inductors into the silicon. So that is the key. Those are the key things that are being done. So in terms of critical thinking, for you to consider, how do the latest power delivery technologies in silicon packaging, semiconductor packaging, address the increasing power demands of modern electronic devices? We have talked about several examples. What potential trade-offs might arise for the implementation? One obvious trade-off is cost. The more complex, the higher the cost, just as an example. But there are other trade-offs. In what ways do emerging technologies for power delivery improve the energy efficiency and thermal management? And how would they influence the direction of the design of future integrated circuits? Let me take the next two questions and I'll go to Jose. What challenges do the latest power delivery technologies face in terms of scalability and compatibility with current systems, and how would these challenges shape the future of innovation? So go ahead, Jose. I see that you have a question.
Yes, thanks, professors. So for the client side, the latest technology in terms of the architecture of the semiconductors use DLVR, digital linear voltage regulator, instead of the
Okay.
fibers. Do
Yes.
you know what is the advantage that offer the DLVR?
I think I mentioned that in a future. I think I remember looking into that in a future lecture. Again, with all of those, the drive is to make the actual design smaller with fewer components and to increase the stability of the VR. So there are several things that we need to do. We need to be able to bring in a higher voltage because and get that higher voltage as close to the devices as possible, which means that the high voltage needs to be stepped down to a low voltage as close to the devices on the chip as possible. That's one thing. And the other thing is we need greater stability of the voltages. And the third thing that we need is that we need the form factor of those components to be smaller. So the DLVRs, those help in all of those areas. And I think I talk about this in a future lecture, very likely.
Okay.
If it's not
Perfect.
addressed, bring it up again. Okay.
Sure. Thanks a lot.
Okay. Good question. Anybody else?
Looks like we have a couple questions in the chat.
Okay.
There's 3.
Okay. Which method is used to deposit the gallium nitride? That's a good question. Commonly, so there are different deposition methods. Now, there are different ways of doing this. One way of doing this is to basically, that buffer layer where it just said buffer is very commonly a proprietary layer, depending on the company. So the proprietary layer, what it does is it tries to reduce the lattice constant mismatch between the silicon and the gallium nitride. So typically what they'll do is they'll deposit that buffer layer. On top of that, they'll deposit the gallium nitride. And the gallium nitride can be deposited by something like a CVD process, chemical vapor deposition process, commonly. Now, you could use PVD as well, but that will tend to not create single crystal gallium nitride. So the most common would be some form of chemical vapor deposition. Now, there is another method that has also been explored, which is basically to create a gallium nitride crystal growth, and then to thin wafer it, make it thin wafers, and then wafer bond that gallium nitride on top of the silicon. So both of these are methods that have been explored and are used by different companies. Okay, so that's the question. Anne Dulé, go ahead, Anne.
Hi, Professor.
Okay.
I'm interested with the MBVR and FIVR earlier. For the
Okay.
MB, the motherboard, the voltage regulator, from the picture that you have shown, it
Okay.
shows that the different chips for the different voltage regulators are actually separate from the core CPU, right? So that means that they are different chips. Is that correct? So it's
The
separate. So you have those chips
yeah,
separate
I'm
from
trying to
the core CPU. Is that correct?
yes. So either they can be like components. So in principle, you can either have the component like the inductor, the capacitor, the resistor that are actually created, like historically they would have been created on the motherboard. That's how these things were done previously, right? So as there's
Mm-hmm.
an increasing drive towards making them smaller, then those separate components are being integrated into one package, which could be different components integrated into one in like a smaller subset of the larger package, or they could be actually built on a separate chip.
Okay, but for the FIVR, they are placed on the same chip, correct?
That's
But
correct.
we
The
know
intention.
that, yeah, we know that analog circuits, VR is of course an analog circuit. They may affect the digital part
Correct.
of the
Yes.
CPU.
Yep. And that is part of the challenges that need to be addressed. So when you're
Okay.
designing these, that's why you need to make sure that the power lines are adequately separated from the signal lines,
Mm-hmm.
and you have circuitry between the voltage regulator. And so a lot of the things that we have talked about are attempts. You can see that the circuitry starts getting more complex. The more you try to address the voltage spikes and droops and so on, the more components you're having to add in. So that makes the
Yeah.
circuit more complex and more expensive, which means the circuit also becomes larger. So now, so that is one drive. The more components they add in, the better you can control the droop and the spikes. But the more you add in, the larger it becomes. So then you have to come up with advanced methods of making these smaller. So previously, you're right. Previously, you could put these either as separate components on a motherboard, like a separate capacitor, a separate inductor, separate resistor, and wiring between all of those. And that's how it was done initially. But then you could move it into a separate VR chip that you put on the motherboard. And then you could later on, they move some of those onto into the package. But now with the FIVR, you're actually integrating some of those things on a chip, but it is challenging. You're right. You need to make sure that you have adequate insulation, separation between the power lines and the signal lines, which is a big issue, right?
Thank you. Thank you.
You're welcome. So let's go back and see what other questions there are. Okay, I see a question from, okay, so I addressed the gallium nitride question. Another one, how is the MIM made? Multilayer will use multi-level. That is correct. Okay, the question basically said, how are MIM, metal insulator, metal capacitors made? And the question was, will the multi-layers use multi-metal layers with multi-insulation layers? And the answer is right. Is correct. That's exactly what you have to do. You put in one layer of metal, and that could be like historically, like on silicon, they would put in a highly doped polysilicon layer. So it's basically silicon, it's polycrystalline, but with high doping. Then they put a thin oxide, silicon dioxide layer, then another layer of polysilicon, polycrystalline silicon on top with high doping. And that would create an integrated chip, capacitor that you can integrate into the die, into the chip itself. But now we're going to more complex situations where you are using like copper, for instance, as the metal because it has lower resistivity than the silicon, polysilicon. And you can use either silicon dioxide or you can use, to make the capacitor smaller, you use a high dielectric oxide. So it could be a hafnium oxide, or there are different oxides that have been explored, tantalum oxide, niobium oxide, hafnium oxide, and combinations of these. Okay, the question continued and said, are these metal layers the same as the metal layer used for the chip? The metal layer, now, commonly they are okay, it depends on the design of your capacitor. So what I mentioned previously with the polysilicon as a metal, it's called a metal, but it's really not a metal, but it's highly doped polysilicon, so it behaves like a metal. So historically, these devices had a polysilicon layer, which is not the conventional metal, followed by silicon dioxide dielectric, followed by polysilicon. That is the easiest to integrate into your chip. But the problem is that those devices tend to have to be larger. To make them smaller, you have to replace them, for instance, with the metal that you use on the chip, which is commonly copper nowadays. In the past, people used aluminum or aluminum with a little bit of copper. So the answer to your question is, to a first approximation, yes, for some of the devices. And for some of the devices, people still use polysilicon, which is not the metal that is used on the chip. So I think that answers the latest set of questions. Somebody asked about the connection of a capacitor and the superMIM. Are they connected parallelly or serially? If they're connected in series, the total capacitance will reduce, while normally we need large capacitors. That is correct. That is that depending on the circuit application, you can choose to use one capacitor if that's sufficient, or if you need to put more capacitances, if you put them in series, the effective capacitance becomes smaller, you're right. But if you put them in parallel, the effective capacitance becomes larger. So in principle, you can put multiple capacitances and then capacitors, and then use it, wire it with the interconnect lines, the metal interconnect lines coming in to make the capacitance lower or higher depending on what you need for your circuit. Okay, I see another question. Okay, power rail, I've answered that. Another one is, what is a T-gate? Okay, it's called a T-gate because of the fact the shape of the metal is like a T. There's a broader pad on top to make contact, and then it comes down into a narrower contact to make contact to the the gate region. That's why it's called a T, because it's got that shape. What's a power rail? We have answered that. I think the other questions have been answered by some of the students as well. Yes, somebody mentioned the myelin sheath, correct? Good point. So in our nervous system, there's an incredible amount of design that goes into the human body in general and the system, all of our systems. And if you look at the nervous system, there are a lot of things that we're learning by looking at the human body and how it works and our nerve systems, how it works. And there's a whole field called biomimetics, where what scientists are doing is looking at the engineering and the design that has gone into all of these different biological creatures, and we're learning from those things and implementing them in real life. One example of that is the current AI revolution. So you may know that AI, artificial intelligence, had reached a plateau, basically a dead end. And for many, many years, there was no progress in it. And then somebody came up with the idea of, hey, how about we create artificial intelligence based on neuroscience, the design that we see in the neurons in our brain. That was a complete revolution. Up to that point, artificial intelligence was dead, really. Then somebody came up with this idea of, let's copy what the design that we see in the human brain, and let's create neurons and layers of neurons. Once that breakthrough happened, we have that resulted in the explosion within the last 2 years of huge numbers of artificial intelligence applications, because we copied the design that we see in human brains, which is orders of magnitude more intelligent than anything that human beings have ever created. So that's a good point. Okay. Anybody else? If not, I shall turn you over to Matt. And if you need to go ahead and take a 5-minute break. I think today's session goes until 9 p.m., right? So
Yes.
take a 5-minute break. And then after that, you can get back to the activities that Matt will drive. Okay?
Perfect. We'll put up a timer. And when you guys come back, if you want to go ahead and open Canvas, so you can access this stuff. I'll throw some stuff in the chat as well if you've had trouble getting into the shell. But we'll make sure you get good to go. So go ahead and open up the Canvas shell if you have it. If not, you could just send me a chat with your email and I can resend that. But I will put up a 5-minute timer and we'll see you guys soon.
Sounds good. Hey, Matt, and just a reminder to tell the students to remember to write down the room number.
Yes.
Perfect.
We got that. Thank you.
Yeah, thank you.
All right. Well, we will go ahead and transition to the activity for today. We're going to send everybody into breakout rooms. And so I know you guys have all been a part of this. It's going to be groups of 4 for these group breakout rooms. Go ahead and log into Canvas if you haven't already. You'll be able to access the article link. There's 2 articles. You guys will assign those articles, split them up amongst each other, so it should be 2 per article. If you have a odd number of people because the group size didn't nail perfectly, just split it up between the 2 articles. And then you guys are going to have 20 minutes, about 20 minutes to read the articles. You'll just read the one that you're assigned, and then you'll have about 8 minutes. I'll post some reminders and some updates on the time, but you'll have about 8 minutes per article for discussion. So a little over 15 minutes total. And then you'll have about 8 minutes to submit your answers in Canvas. There are a couple questions that you'll see in Canvas. You only need to submit the answers to your assigned article. And then please make sure once we split up into the groups, please make sure to write down the group number that you're assigned to. That way, if I know people are in and out a little bit, if you drop out of the Zoom for some reason, we can put you back in the same room. If you forget, we'll randomly assign you. It's all right, but that will help. That'll help the discussion. Jose, I see a question.
Thank you, Matt. I just wanted, if you can say which ones are the articles to see if I'm correctly in the day.
Yes. The first one is design considerations for ultra-high current power delivery networks. Let me, I'm actually going to throw that into the chat. I don't know if this will show up as a link or not for you. It looks like it did. So that's the first article. And then this one right here is early STEM education, key to growing future chip workforce. And this is question number 2 or article number 2. Once you guys are in the breakout rooms, I will broadcast the discussion questions in case anybody's not able to access through Canvas. So with that, let me open up some rooms. Let's see, we got 121, 30 rooms.
Matt?
Yes.
We have how many minutes all in all? So 20 minutes for reading and then 15 minutes for discussion.
Yep. So we'll have everyone will come back. I'll close the rooms at 8:49. You guys will have about a minute to kind of exit your room and come back in. We'll have some kind of closing, some final thoughts, and announcements before we go. So yeah, I'll broadcast some updates like, hey, if you haven't already started discussing, go ahead and do that. If you haven't started discussing the other article, go ahead and do that. So I'll give some cues along the way. Awesome.
Thank
cool.
you.
Well, we will see you guys soon. If you guys are still in the main room, if you could go ahead and join your breakout room, that'll help the discussion. For those of you still in the main room, we got about 9 minutes left for the reading for the articles before we jump into discussion. So if you guys can go ahead and join your breakout rooms, and then we'll keep going. For any of you guys left in the main room, we've started discussions in the breakout rooms. So if you can go ahead and join the discussion group that you've been invited to and hop in on the discussion. Thanks. Those of you guys in the main room, we got a little less than 7 minutes. If you haven't already, go ahead on the Canvas shell and you can submit your answers to the questions. You only need to answer the questions for one of the articles. So if you were in a group and then fell out and then came back in a minute ago, just do whichever article you were assigned within your group. Otherwise, pick one of them and go ahead and fill that in. And then we'll invite everybody back in at the end of this time. All right. Welcome back. Looks got a couple people jumping back in. Excellent. Perfect. Looks like everyone's back in the room. I'll pass it back over to Dr. Theodore for some last thoughts about the articles.
Yeah, actually, Matt, why don't you go ahead with your announcements, and then I'll do the articles.
Sure, absolutely. Awesome. Well, hey, like you guys know that have been in these programs, this whole thing has been recorded, and so it'll be uploaded as an announcement that you'll be able to find on Canvas tomorrow. So keep an eye out for that if you want to watch the recording. Also, if you did not have time to finish the submitting your answers on Canvas, that is open until 5 p.m. tomorrow, Arizona time. So make the translation for wherever you're at, but it'll be open until 5 p.m. tomorrow. So take your time, but do make sure to get those in. That's all I got.
Okay, perfect. So I'll go ahead and mention, first of all, thank you to all of you, to the students, and to Matt. Matt, thank you for your help. And to all of the students, thank you for the pleasure of your company, if you will, this evening. It's been actually 3.5 hours, so it's a bit exhausting session, I'm sure, for all of you, but I think it's worth the while. So thank you, and it's been a pleasure. So I'll go ahead and quickly provide my thoughts in response to the questions associated with the articles. The first question is, when servicing a DUT, device under test, what is the function of the optimized power delivery network? We have discussed this to some extent.
Để em nói xong đi rồi đi ăn cơm luôn. Chưa.
Okay, we've discussed this already. The key benefits of an optimized power delivery network are to transfer power efficiently from the voltage regulator module to the device under test, basically the device, the chip, while ensuring that the supply voltage remains constant within a very tight tolerance band. So by doing this, you minimize voltage ripple under the load, and you provide a stable and clean power supply that helps the chip to operate in a manner that is satisfactory to the customer. The next question, what is the novel via placement scheme in that article, and what's the rationale for it? The key thing that they did was they offset the device vias, the device under test, DUT vias, towards the corner of the device. And the idea basically was to create a straight, easy channel for current flow to the core of the device. So by doing this, basically, instead of having a very convoluted path, they are providing a simpler path, they state. And this reduces the electrical resistance in the power delivery path from the corner of the chip to the core of the chip, which is where a lot of the power demands are. So you're reducing both the electrical resistance as well as any inductance associated with long and convoluted lines. That's the key benefit to their scheme. The second article was dealing with the rationale for building a domestic workforce. Of course, this is from an America-centric viewpoint. And so this may not apply to some of the countries that are being represented here in the students. However, there is strong interest in America partnering with each of the countries that you represent to have good, strong packaging industries in your home countries as well. So some of these can apply to the countries that you're in. One of the key issues in the semiconductor industry in the US is that there is a workforce shortage. In other words, the projected demand for semiconductors is significant. We have a lot of manufacturing factories, but we do not have enough domestic workers available for those fabs. So we're very dependent on students coming here, typically in grad school and so on, master's, PhD students, but there's also a need for undergrads and for technicians and so on as well, who may have a 2-year degree. We are dependent on individuals coming from other countries to our education system to create the workforce that we need. And that's kind of up and down. There are times when that supply is able to meet the demand. There are times when it's not able to meet the demand, because that also depends on what's happening locally in each of those countries. So that article is basically saying that the US needs to have a better focus on attracting children to science, and that's needed for purposes of national security, filling the high demand jobs, and also the semiconductor industry provides good salaries compared to many other industries like the retail industries and so on in the US. So that's the rationale for building a domestic workforce, because the projected needs for semiconductors are only going up over time. And that'll become more as more AI, artificial intelligence, is built into everything, like everything into cars and into refrigerators and so forth. The last question is, what are the challenges in attracting children to science, technology, engineering, and math subjects? That particular article, again, I'm speaking from a perspective of having lived in Asia. I've lived in other countries and then also living in the US. So that's why I'm speaking from a broader viewpoint. This article seems to be focused primarily towards the US, but this could apply in other countries. My experience in a lot of Asia, for instance, is that students tend to go where their parents direct them to go because there are well-paying jobs in those fields. Like when I was growing up, for instance, in India, my sister and I were provided only two alternatives by my parents. You can either become a doctor or an engineer. There are no other alternatives. So I was a bit queasy at the sight of blood. So, I mean, I did look at going into medicine, but decided to switch and went into engineering as a result. My sister, on the other hand, was okay with blood, so she went into medicine. So I think the cultural drivers in the US are different from the cultural drivers in a lot of Asia, from what I've seen. But anyway, this article is relating specifically to the US. And in that context, one of the issues in the US is that a lot of children are not interested in STEM. They're interested more in things like video games and sports and smartphones. And so this article is making the point that in order to make science, technology, engineering, math more interesting to the students, that the US educational system needs to see a connection, make the connection between things that the children find interesting, like smartphones and video games and sports, and make the connection to the semiconductor industry. And there's a need to increase the awareness among parents and teachers, and also about the opportunities in the semiconductor industry. Those are the key points that I got from these 4 articles. Okay. So that's basically what I had. Do any of you have any other further questions? Okay. If not, we're 2 minutes before 9 p.m. and I'm completely fine with ending here. If any of you have additional questions, you're welcome to stay on and ask them, or alternatively, we will be meeting tomorrow. And the current plan is that I'll be lecturing tomorrow night as well. You're welcome to ask your questions then as well. I know it's been a long evening for you, or a long morning, depending on where you are. And I hope you have a good morning, afternoon, evening, or night, depending on where you are. Thank you for your time. Bye for now.
Thank
Bye-bye.
you.
You're welcome.
Thank you.
Yeah, my pleasure.
Thank you.
Absolutely.
Thank you, Professor.
Thank you so much.
Thank you, Professor.
Welcome. Thank you.
Thank you,
Have a
everyone.
good. Yes,
Thank you.
thank you.